Kate Sepato, who's with us, and Bill, our main CISM developer. Welcome. Thank you for joining. And before we start, I would just like to remind everybody about our code of conduct. Pretty much be courteous to everybody. There's no bad questions here. Everything, it's a friendly group. And so if you don't know anything, don't be shy to ask. We're here to help. And we're here to have like good conversation, share the air with people, don't monopolize the conversation when you're in the discussion. And show appreciation and acknowledge teamwork as much as you can. As a reminder, this session is being recorded, so it will be made available once the meeting is over to everybody to see. So just for you to be aware. This is the agenda for today. Everybody is going to have, all the presenters will have 15 minutes for their talk, 12 minutes for us talking, and about 2-3 minutes for questions. I will be monitoring the first session and maybe the second. I will see with Kate. Please, if you are in person, mute your cell phone. And for people that are online, if you can join the meeting using companion mode. And I'm saying this and I couldn't find a companion mode option on the link. So, but maybe it's just me. Also, I would like to thank all of our administrative and multimedia team for making this possible. They've been working tirelessly to make sure that everybody would go smoothly, and it's going very smoothly. If in person, you'll see Kayla is in person to help us. Elizabeth is and Daniel online monitoring everything. So thank you so much for all of your help. It's always very appreciated. Okay, I'm the one starting the first talk of the session about giving you some Lendice updates. And I'm not going to go into the scientific updates really, but keep it about, it's going to be mainly about CSM3 and CISM, where we are and where we're going forwards. All of the science updates will be given by the amazing speakers we'll have this morning. Let's see. All right, let's get started then. Okay, in this talk, as I just said, I'm going to tell you a little bit about CSM3, where we are right now in terms of releasing the model, so the timeline, the associated Lendice coupling in CSM, where we are, and a quick update on Lendice diagnostics within CSM. I'm then going to talk about CISM, the release, and some ways to create some input files for CISM and some future events happening in the CSM community. So let's start with CSM3. It's been a long and spinning wheelie road, but we're getting there slowly. So right now, CSM is in active development. We are at the stage where all the science in CSM is being frozen unless it's for bug fix. The current state of the model still has some biases in the atmosphere, so it's not quite ready to perform any transient simulation or to do any spin-ups of the ocean. And for that matter, we have not run strong diagnostics for the Lendice because the atmosphere is not quite there yet. However, the goal is to have a model by April. And hopefully then by April, we can start spinning up the ocean, which is going to take about a couple of months. And then everything would be ready for software engineering, testing, documentation, simulation. We're not really, the chief scientist is not necessarily very worried about a strong release date for the model itself. But what we would really like to obey by is to perform the CMIP 7 deck and fast track simulations, which need to all be submitted by the beginning of January 2027. So this is the timeline that we're going to obey by. In terms of Lendice timeline within CSM, so we are actively focused on Greenland right now, and Antarctica is it's in our mind, but it's we're being asked to have Greenland evolving fully coupled by default if possible. So this is what we're actively working on. And this goes hand in hand in diagnosing and reducing the surface mass balance biases in Greenland's couple system. And once this is done, we'll be able to create, hopefully, a sensible pre-industrial Greenland spin-up for the couple runs. Ted is going to talk about this, but the CISM evolve, or what we used to call it one-way coupling, has been replaced with a data land ice, and she's going to tell you more about it. So in terms of Greenland, this is work in progress. We're actively working on it right now, and it's going to hopefully go smoothly for the couple release. And when it comes down to Antarctica, we are also looking at the biases in the atmosphere, but also in the Southern Ocean. It's going to take us a little bit longer compared to Greenland. And once we think that there's going to be the biases are reduced enough so that Antarctica can live within CSM, then we'll work actively on the two-way coupling. In CSM2, there is a diagnostic package that users could run and create diagnostics with CSM, with other components of CSM. Unfortunately, with Derecho, this tool could not be ported, or could, but was not working anymore. And so there's a new effort called the CSM Unified Post-Processing and Diagnostics, also short for CUPID, that's being led by Tegan King and Michael Levy here in NSF NCAR and CGD. And it's supposed to be a one-stop shop that enables and integrates time series file generation, data standardization, diagnostics, and metrics for all CSM components. It's supposed to be a collaborative effort. It's meant to simplify user experience of running diagnostics. The tool can be directly called from CUPID itself, which is on GitHub, and you can run all component diagnostics from one tool as either part of the SIEM workflow in CSM or independently. Up to you. It's a shared Python code in a standard Conda environment across components. And right now, so it's an ongoing effort that people are working on when they can, and it's ongoing. They're working on having CSM workflow, having CUPID run as a CSM workflow or independently. You have a few key metrics that are available for land ice, the atmosphere, and the land, and you have examples for all components as well. There's basic time series file generation that you can do at this point, and the documentation is an ongoing development. The entire community is invited to contribute to GitHub, and you have the link here to the GitHub page. And please, if you plan on contributing to this diagnostic effort on the land ice, and please let us know so we can coordinate this effort. In terms of land ice diagnostics in CUPID, so this is an example of what is there you would get if you're trying to compare one of the latest CSM3 run that is being done right now to diagnose the couple system. It's a notebook that only looks at the PI controls, the pre-industrial controls for surface mass balance, and the example here on the I don't know if my cursor works. On the left-hand side, what you have is the climatology, a 40-year climatology of the latest run. It's run 121 of the surface mass balance, and we compare it to a 40-year kind of climatology of the MAR regional model. And then it puts the difference to get the biases. And then on the right-hand side is the time series of the last 40 years in blue of the PI simulation, the PI control simulation to observe the variability, and we're plotting the mean of this data in the dotted blue line, and in black, the mean surface mass balance of the MAR model. So this is going to evolve. More is to come. Right now we are we're working on a notebook to analyze historical runs for annual and seasonal averages and climatology. And we're also going to have a notebook analyzing other variables such as precipitation, runoff, and surface temperature. We're almost there. Okay, moving on to CISM now. In CISM3, we have a plan in place for future CISM release. You might be familiar now with that we've been developing glacier capabilities. The paper has been submitted about the framework of running CISM for glaciers. It's been accepted for review not too long ago, last week. And then we are trying to create a good stopping point for the science that's being currently developed for ice sheets in terms of calving and hydrology. And so hopefully we can have a good stop by the spring of 2025, in which we're going to create a science trees to then focus on more code cleanup, season testing, documentation, and streamlining input file creation to then have a full release of CISM 3, hopefully by winter 2026 or before. Meaning when we say winter 2026 is more like January to March 2026, not like December 2026. In the meantime, we are also working on additional glacier capability, but also glacial static adjustment and solid earth coupling with CISM. And Kate is going to tell you a little bit more about this. Okay, we've received many requests about input file creation for CISM runs, and so it was time to create something for the community to be able to use and create their own files should they want to. And what I'm going to talk to you here for a couple of minutes is the workflow that everybody here can follow to create their own CISM files if they want, should they choose to. So the way it starts is like you need to define the CISM grid file, your grid on CISM. Right now, by default, we're using the grid that's used by SMIP6 for many reasons. And so what you do, you start by creating your thickness and velocity grid in Cartesian space, and then you interpolate all of your observations that you'd like to use to do your spin up. And the data that we typically use in CISM is topography, thickness, bed topography, masks, surface elevation, surface mass balance and air temperature, geothermal heat flux, and we also have ice velocity for diagnostics. And for Antarctica, we need summer forcing and some ocean basin number. And you optionally can also generate mass change rates and an ice domain mask, which defines the boundary in which CISM will evolve. And once you do this, you can then define your input file in CISM and put it in your configuration file. Now, there are several ways to define an input file in CISM. You can have all of your data in a single file and then define this file in the CF input section of your configuration file in just one name. Or you can have several input files in which you split the data that you want to run with in several files. And then you just need to call several CF input instances in the configuration file and name them all, and CISM will read them in order as they're received. So one of the advantages of doing this is that, for example, let's assume that you would like to increase the impact of geothermal heat flux on your system. You can just swap all the various geothermal heat flux data that you have without having to redo your input files. So there's notebooks available to do all of this. It's one notebook per task and per data type. And right now, the data it's been used to create Antarctic input file only. But for Greenland, it's coming, and you'll be able to use the same notebooks to do this. I've put them all in one directory under Rachel. You have here the path for them, and this is a snapshot to show you that it's there, and they're not empty files, I promise. So please, if you have an account under Rachel, feel free to use them, and just be aware that they're still in development. So you can say, hey, the coding is not great, and well, yeah, that's fine. But as you use them, please share your feedbacks for improvement and how we can make them more user-friendly. And just to let you know that everybody can do many things with the data. And right now, we did not incorporate any notebook for smoothing the data. So this is something that for now you're going to have to do on your own. We have some, but everybody does their smoothing differently unless we have a more generic way of doing them. or like more options, we'll leave it that way. We will incorporate these notebooks into the CISM code eventually. We'll need to talk about more how we're going to do this. But please don't hesitate to contribute to this effort, and also to with additional data sets that you'd like CISM to use for science. A couple of future events to come this summer. There is a CSM workshop taking place from June 9th to 11th. It's the 30th anniversary of the CSM workshop, so we would like to make it special. So if you can, please come in person. It would be very great to gather the community to see everyone. Additionally, the CSM summer tutorial is going to be from July 7th to 11th. So for everybody who would like to know more how to use CSM, please register. The registration has been extended to February 7th, and decision on attendance will be made by April 18th. Okay, and thank you. With that, there's more contact information here. If you, as usual, if you have any question or like to reach us, Kate, Bill, Miran, or myself, don't hesitate to do so. Thank you so much, and I'm welcoming any questions. And if you're online, please raise your hands. And if you're in person, raise your hands too.
This is the Mines Glacier Group first year PhD students.
Yay, welcome.
That's
awesome.
Bottle curious, so I thought maybe
Awesome.
learn more about CISM and glaciology. So she picked the interlopers.
No, you're welcome. Glad you're here.
Yes, Michele.
Hi, thanks for the presentation. Very nice. I have a bit of a somehow lateral question regarding the CISM new input file. So if one would like to run like a CSM or for instance NORISM with this new input file,
Make the screen bigger.
is it enough to define the new script CISM grid files, or one should also calculate the mappings offline and so on? Do you know about that?
So right now, so you'd like to generate your own grid file for CISM?
Yeah, for example, I mean or maybe just to switch to the new grid as you did.
A little bit bigger.
I'm not sure I quite understand the question.
So the idea is that of course you can define a new CISM input file, but then if you're running fully coupled, then of course you need the new mapping file from all the land component or ocean component to CISM,
right,
because you have a new grid basically. I assume the grid is different. So I was wondering, I know that the new coupler is calculating like lots of mapping files and stuff online differently from before, and I was wondering if you have like an overview of what one would need to do when it's changing these input file and grid file as well.
I'm not sure about that actually. Do you know, Kate?
It's not something we've tested very much, but my thought is that you don't need to do much.
Okay.
I think if you set up the input files and grid files for CISM correctly, the trick would be just to specify that in the comp set and the grid resolution, which is 2 XML files that you have to specify the grid information in, and then the rest of it is done in new OPSI. So we don't need to do the mapping files anymore, from what I've heard.
And if you need any script files, I created a notebook that does just this with the CISM grid that you'd like to create. So it's there too. But right now, by default, Greenland is 1 4-kilometer grid in CSM, so it works pretty well. And
yeah, that's really great to have something to share. Thank you for that. Yeah.
Yeah. Thanks. Any other questions? Okay. If not, we'll move to the next talk. Kate, would you like me to present your talk, or would you like?
Let's see if I can share. I think you need to. I think that worked. Okay, so see if I can do this. Cool. That worked really well. All right, welcome everybody. It's great to see so many people here today and online. My name is Kate Calder. I'm a CESM and software engineering liaison for CISM Group. So if you guys have CESM questions, you're welcome to contact me and talk about it. I'm going to talk about a lot of work that we've done in the last few months here this morning from a lot of different people. I tried to make a pretty comprehensive author list here, but there's probably more people than I could possibly name going into this right now. So one of the problems with software engineering talks is that they tend to be very text heavy. So I tend to have funny pictures that don't have a lot to do with the text. This year I leaned heavily into penguins because penguins make me happy. It doesn't have much to do with what I'm actually talking about. So don't try to really coordinate the penguin to the slide. Just accept the penguins. So let's see, there we go. I'm going to be talking about the updates that we've made to CISM, mostly to support the changes for CSM3 and the release going forward. And I apologize, this is a little bit heavy into people who are familiar with CSM. So it may not be, I didn't know there was grad students coming. But I can try to explain things as I go as well. There's going to be some talk about the changes that we've made both to the coupling between CISM and CESM, the new data glacier component that we've added, and then some other CSM updates that have impacts on CISM, like adding the timestamps to our point of files and changing managed externals. Some changes to the supercomputers that we have to deal with, and then some work that we're doing right now that I think Michaela might be interested in about running CISM standalone within a CSM framework. So let's talk first about the data glacier model. So previously, this is a sort of a complicated, I don't think you can see my pointer, can you? All right, well, this picture here is a complicated overview of how the coupling worked between the ice sheets and the rest of the CSM model in CSM2. And one of the things you'll notice there in the middle is that there was a CISM no evolve and a CISM evolve option. So CISM no evolve was basically the ice sheet model, but it didn't do anything. It just would have a certain size and mask and send that back to the land. So the land model would handle all of the ice fluxes and the runoff fluxes and the snow fluxes instead of CISM doing it in that case, which meant that the land model had to know if the ice sheet was active or not, and then send different information depending on that case. Because the season, so I'm getting ahead of myself. What we've done is instead of having the CISM no evolve option, we've created an offline data component that basically acts like CISM. It can take any of the fluxes that would be handled to the active ice sheet and manage it in a way that makes sense for an active ice sheet slightly better. So that means that we've just basically changed those two boxes and the complicated extra fluxes to a more streamlined coupling that looks more like this. So CLM, as far as it's concerned, will always be dealing with an active ice sheet. And then CESM just handles what's going on between the two in the background. This is cheaper and easier to run than CISM no evolve. Previously, you had to compile the entire ice sheet model, regardless of if you wanted an active ice sheet. So now you just have this little data model instead. And it's available in the newest CDEPS tags going all the way back to CDEPS 1.0.53. So you can look for that in your CESM checkout if you're interested in using this. One of the issues that we had previously with CISM no evolve mode and CLM handling all those fluxes was that the seasonality of runoff was not correct. So there were months when the amount of melt coming off of grid cells around Greenland were higher than the amount of snow, and CLM would just send a negative water flux to the ocean to balance that. So basically it would try to suck water out of the ocean to balance the ice melt in Greenland. And that doesn't make ocean modelers happy. It's not realistic. So when we added the data glacier model, we've added sort of a hole filling algorithm that allows us to balance the excess melt during certain months with the excess snow coming in. So that has reduced the amount of negative. Actually, it's gotten rid of negative water fluxes. That was a really nice feature for CSM3 going forward. Also rerouted the ice sheet runoff through the runoff model instead of sending it directly to the ocean. So previously, the ice sheet for both liquid and solid runoff would have a mapping file and send it directly to the ocean. But that was starting to get really difficult with all of the different ice sheets. We have 2 or 3 different ice sheets in the model, and each one of those ice sheets can have multiple different grids. And now we have multiple ocean models, mom and pop, and each of those models can have different grids, including higher resolution refined grids, things along those lines. It becomes a very difficult task to try to match all of those up, where the runoff model can handle all of that much simpler. So we rerouted all of the CISM runoff to one model, the runoff model, and now we don't have to worry about all of those infinite mapping options, and it simplifies the fluxes much more. So this is a picture of CSM fluxes going forward, and you can see much better than what we had to begin with. It's much more clear. The runoff, the heat and salinity being transferred from the ocean mom here back to CISM is something that we're working on actively right now. It's hoping it won't be probably for the CSM3 release, but something 3 point something in the future will have the ability to take in that information from the ocean. Sorry. Okay. So just running through a couple other updates that impact CISM. I kind of mentioned these previously. These are AI generated baby penguins. I couldn't decide if they made me happy or scared. They're kind of creepy. All the restart pointers in CESM have been changed to have a timestamp associated with them. Previously, if you had a restart file, our pointers just pointed to the most recent restart option. But now you can specify a specific date for your restart in your run directory. So you can have multiple different restart available in the run directory for the model, which is a really nice feature. We've changed manage externals. Oh, these are all Jim Edwards work. So Jim Edwards worked with us to do that. Manage externals has been removed. So previously, we use an in-house tool to bring in all of the external software to CESM to prepare it for building. And that has been removed and replaced with basically true submodules in Git now. But we use a tool called Git FlexiMod to make them more user interface similar to manage externals. So if you guys have any questions about checking out the most recent versions of CISM Wrapper or CSM and how to use Git FlexiMod, you can let me know. It is a little bit different than manage externals, and the code tree looks a little bit different because of the submodules. And then I wanted to let everybody know that the iFort Intel compiler is basically being deprecated and removed from Duratio, which was the big Intel compiler that we used for CISM. And we're going to be moving into the IFX Intel, which is their updated One API compiler in the next few weeks. So I wanted to finish up this talk by talking about this testing that we're working on right now, which I'm pretty excited about. So previous to this project, there were 3 testing modes for CISM. There's the CISM standalone test using the Python scripts that come with the checkout. Those are pretty awesome, and they work well. There's also an external tool called BATS and LibKit that basically replicated those Python scripts and testing in build scripts, and added some more functionality to be able to handle baselines and comparisons and verification and validation. But the code was replicated and separate. So if you wanted to update either the tests or say the build modules on Duratio, you had to do it in both places. And then we also have the CESM and SEAM test. So SEAM is the coupler user interface for CESM that lets us describe all of our experiments. And it has a lot of very powerful testing tools within it that could do everything that the CISM standalone test and the BATS LibKit test do as well, but with fewer well, I'll explain why we're doing that here. So we're going to move the SISM testing into the CSM testing. The CSM testing is always updated for the computers that we have here at NCAR as they change. It includes full test suites that can be run with the baseline comparisons with just a single command. So you can specify a whole lot of different testing options in a very powerful method. And then the CSM workflow includes archiving these baselines for future easy comparisons. So it got a lot of benefits over the other two methods. And this way we'll be able to keep all of the code and the modules and the testing specifications in a single place instead of spreading it out over 3 different repositories, which makes my software engineering heart happy. So I added a link here to talk about the testing cases. It is a little complicated. It has a bit of a spin up and a learning curve. So that's going to be part of the work of this project going forward. I'm not going to explain how to use them all right now because I'm running out of time, but you'll probably see a talk about that maybe next summer. So this is a work in progress right now. And ultimately, the goal is to support within CESM a version of SISM that is nearly identical to the standalone testing so that we can get the same answers regardless of which user interface you use to run those tests with. But this means that we're going to make some changes to how SISM can be run in CESM, offering an alternate build and run pathway through the code than what is in there currently. So right now, SISM is integrated into CSM in a fully coupled manner that expects data forcing from CLM. It doesn't read in its own forcing files like the ones Gunter was talking about making. And so we're defining a new type of TCOM set that supports SISM without any of the data external necessary and can read in all of its information the same way that SISM standalone would. And this means that going forward, we'll have the option to run SISM standalone in the same way that everybody does currently, but using the CESM case control system, which is a very powerful tool for machine support and experiment documentation. Hey, okay, that worked out well. Okay, so as a summary of everything that I just said with some really cute AI penguins, these are less creepy, I think. I don't know. So I'll stop there, and if there's any questions, I'm happy to answer for this talk right now. Thank you.
Thank you. Any questions for Kate? Katie?
Oh, you can go ahead, Michele.
Oh, yes. Very nice, Kate. Thanks. I was curious. I might have lost one bit because my connection was not working great. So with the idea of removing these negative freshwater fluxes, which is really nice and important to do, in a context of like warming scenarios, I couldn't quite understand what would happen, like if there is a melt over like the data GLC. Would like nothing be done with that, or I didn't quite catch exactly what would happen in that context.
Sure, I didn't go into a lot of detail as part of this talk, but basically we use an in situ hole filling algorithm. So the excess snow in the center of Greenland is used to balance the excess melt around the edges. In a strong warming or collapse scenario, that may not hold up. So that would be something to look at in a future issue, but in current simulations and the PI simulation, it's reduced the negative fluxes to 0 from Greenland.
Oh, okay, thanks. Cool work.
Thank you.
Any other questions for Kate? And just to remind everyone, if you arrived late after I said this, again, this is a friendly space. So there's no stupid question or easy or hard question. Feel free to, if there's something that you didn't understand, didn't get, please feel free to raise it.
I do have a question.
Okay.
Yeah, absolutely.
So what was handling the runoff before? Now we've rerouted it.
So in the great. So in the no evolve situation, the land model handled all of the runoff.
Okay.
In the evolve situation, SISM would send all of its runoff directly to the ocean. And
see.
that was why we had to handle all of these mapping situations between the different grids. And it started getting really difficult. So just moving to the runoff model instead, now we only have to worry about mapping to the runoff model,
Mhm.
which doesn't change its mapping files very often. So that's much easier. All right.
Okay, so our next speaker is Kate.
I get to go again.
She's shifting gear now and talking about our effort to with Solidus.
Okay.
What?
We're good? Okay. All right, so I'm going to give one more quick talk about another project that we're working on here where we're hoping to couple a solid earth model into CESM. This list of authors may not be, you know, the full list either. It's the group that I've talked to so far about this project. So, you know, if you are not listed here, let me know. I can start adding you into these talks too. So this is a quick overview of what I'm gonna, as my son says, yap about here for about 10 more minutes. We're going to talk about what GIA modeling is, how a GIA or sea level is modeled in CSM currently, and what we're hoping to do with SITCOM SVE3 and our collaborators at the University of Colorado Boulder in the future, and some of our plans for this project. So GIA stands for Glacial Isostatic Adjustment. I'm going to put on my glasses so I can read what I wrote here. This is as ice or water loads the Earth's surface, the crust and mantle can be deformed with lithospheric displacement and flow. And this causes a lot of different topological changes on the planet. So I like this figure because it shows the ice sheet here pushing down, and I'm sure a lot of people here are very familiar with this, and pushing up the Four-Bolt Formation on the edge of the ice sheet. But then once ice melts or retreats, then the lithospheric flow reverses and the crust balances back because of isostasy, and the Four-Bolt collapses. So there's a lot of people who work in this and model GIA changes because it has a lot of large impact on the United States, which exists geographically around the edge of the Laurentide ice sheet and has experienced a lot of this Four-Bolt activity. So this is a kind of a nice figure that I found that has the east coast of the United States here with the population centers in dark red, paths of hurricanes as they come onto the east coast here, and then the relative rise in sea level at various latitudes that people experience. And you can see here around the Delmarva Peninsula and the Chesapeake Bay, they experience much higher relative sea level rises compared to other places because the Four-Bolt is also collapsing. So that subsidence of the coastal region makes it seem like the ice or the sea level is actually rising much faster there than in other areas. And that's dangerous for all of these highly populated centers in the United States. So taking that into account, you know, how is GIA or sea level modeled in CSM currently? We're the foremost climate model, or one of the foremost climate models the United States produces. People look to us for information on sea level rise and the impacts of climate change. And we actually don't take this into account at all. So this is another figure of CSM3 as it's currently being worked on. You can see that it has this hub and spoke architecture for the model. So we use a coupler, which we call actually NUOPC, but it's encased in this SEAM, the Community Infrastructure for Modeling the Earth software for user friendliness. There's a lot of acronyms here. And then that coupler talks to the atmosphere, which includes the chemistry and the high top atmosphere. It also talks to the sea ice, it talks to the land ice, it talks to the ocean, the waves, the river, and the land. And each one of those sends its fluxes to the coupler, which sends those fluxes out to the correct place. And this is another figure here from the Goddard Flight Center that shows, you know, the complicated processes within the Earth system that are included in most Earth system models right now. And one of the things you just don't see is any sorts of changes in isostatic land uplift or subsidence. So with that in mind, how is GIA modeled in CSM currently? It's not. The atmosphere and the surface, the topography is always considered to be completely static in CESM. We've come into trouble with this in past transient simulations with ice sheets because just the simple fact that the ice sheet is losing altitude as it melts, it can't be communicated to the atmosphere while it's running. It always expects the surface to be the same. So when the model pauses every 10 years or so, we run an offline tool to update the surface of the atmosphere. And that's caused us a lot of issues. I call this the topography updating problem in CESM. So this is definitely, the side that I'm coming from here and hoping to address. But there's a lot of other reasons why we'd want to add in this modeling capability to CESM. It's just so many things are considered absolutely static and non-changing in this model, including the mass between the land and the ocean and the actual sea level on the surface. When we want to run this model through long paleo simulations or into long future projections, the fact that we can't include these changes in the Earth's surface that are very important for human settlement is very disappointing. So how could we add GIA to CESM? And this is the project that we're looking at doing here. And that's to bring in the SITCOM SVE solid Earth model into CESM as a component. So I love how there is space in this diagram over here, just perfect size to add in solid Earth. And if we can add in this as another couple component in CESM, it'll allow SITCOM to actually couple to land ice, which would be a first step, and then to the rest of the model to add this information into our fully coupled Earth system simulations. So I'm going to talk a little bit more about SITCOM SVE here. This is a really nice open source 3D, very efficient finite element model for modeling the solid Earth. And up here you can see their most recent paper for SVE3. So I recommend everybody, if you're interested in this further, to take a look at that paper. This is one of the figures from that paper showing the finite elements that they use to model the mantle. It can take prescribed loads from ice sheets and ocean tidal forces and then solve all those 3D equations for appropriate isostatic adjustment. It's very efficient. It scales very well into ratio. It's not currently coupled to any other ESM. So we're really excited to have the possibility to bring this into CESM so that we can get this coupled to SISM and the rest of the Earth system. So how would we go about doing this? This is my very vague outline of how this project is going to proceed. But we've already made a nice first step in bringing SITCOM SVE3 into GitHub and source control so that it can be mapped to CESM as an external, similar to all the other components. This is another figure of this hub and spoke architecture that we use in CESM, but this one is more focused on the coupler. So we use so many acronyms. The ESMF nuopsy driver mediator in CESM. And I don't even know what most of those stand for, but the point of this figure is that this driver mediator takes only a very small software cap. It's usually one file or two to communicate to each of these large code-based components. So as we bring in a new component, we need to add that thin layer of the nuopsy cap to interact with the component and to send the appropriate fluxes back and forth. And nuopsy can handle most of the rest. Like I was telling Gunter previously, if we define the grids appropriately for nuopsy, it actually generates the mapping files for us online, which is really nice. And it's one of the things that we're really going to leverage in this project going forward. Then we have the next step that I'm working on right now is adding the build scripts, including the possibility of a Fortran API to the C code and SITCOM SVE. Currently, most of CESM is written in Fortran, but there are some tools that are written in C and have, so this isn't unprecedented. There are other pieces of software that are included in CESM that are written in C. And SEAM does include now a package called FTorch, which is a Fortran interface for C packages to run machine learning code in CSM. So I'm hoping to be able to leverage that for this project as well. This isn't exactly machine learning, but that bridge between Fortran and C has been explored in the past, and I believe that it's not new territory. Then we'll need to add in this new OpsiCap and declare the fluxes for the mediator, add code to accept loads or to accept isostasy and SISM. Some of that has already been done, but I'm sure that there will be more work in that area to go forward. And of course, the testing, debugging, and refining, which will be a fun process. So here's an overview of some of the issues we'll be facing. And like I said, the Fortran and C compatibility is not super simple, but it's not something that hasn't been done before in CESM. And we're hoping to solve this topography updating problem at runtime with this solution eventually, but that can become a very complicated issue with the atmosphere as well. And going in the next bullet, if we want to bring this into full CESM eventually, it's going to require updates and changes from every single component to become more flexible with their definition of what the surface actually is and where it lives relative to their code, which is probably going to be an interesting and thought-provoking process. But it allows us to do some really exciting new science. This is just a simple figure showing the simulated radial displacement and east-west displacement from this model on the surface of the Earth. If we bring this sort of information into CESM, it'll allow us to have some much better views of isostasy for long-term paleoclimate simulations, for future projections of coastal subsidence, even this atmospheric circulation impacts on ice sheet growth and retreat, because we'll have a better view of the topography of the ice sheet from the atmosphere. And then I started, just thinking of cool stuff that might be interesting in a fully coupled simulation, like, long-term impacts on the vegetation and carbon uptake for land as it is moved via isostasy. So that's my talk right now. This is an AI generated picture, so I thought it was pretty, but it's definitely got some weird stuff to it too. If there's any other questions or comments, I'd love to hear your thoughts on this project. Thank you.
Yep. Do you have time for questions for Kate?
Very naive question. The two land models that are referenced in the kind of spoke wheel, what is the difference between the two, or used?
Sure. Now, let's go back and see exactly. So there's really only one main active land model in CSM, and that is CLM.
The previous one.
The previous one. Let's go all the way back here. Oh, no, that's right here.
Fates and CTA 6.
So previously known as CTSM, CLM, it's now CTSM. Fates is I'm not great at this, but Fates is a subset of that land model. So it's included in CTSM, and I believe that it's
Ecosystem.
vegetation, model. So it's kind of like the chemistry in the atmosphere. It's a big part of the total model, but not its own. There's also, so this figure doesn't have it. The other one, must have been my other talk, includes the stub and data models that we have available. So yeah, here you can see the land has CTSM, and then we have the data land module in the CESM that is just reads in forcing files that mimic what the land would do if you don't want to run a fully interactive land at that point. Does that make sense?
Yeah.
Cool.
Thanks.
Yeah, no worries.
Yep.
Are there-
H1, go ahead.
Yeah, hi, Kate. Yeah, thank you so much for this really exciting big picture for the future adding Sitcom SV to CSM. And I have a very basic question about right now in CSM. You mentioned for the atmosphere, I mean the profile between the atmosphere and ice sheet. You mentioned it's static. I suppose even though right now in CSM the topography is fixed, and then due to the dynamic in ice sheet itself, the ice thickness, I mean the elevation also varied. So in this way, the atmosphere, the height of the atmosphere also should evolve with time. So I don't understand the static you mentioned in that part.
Right. So SISM, when it's fully evolving, it does change the ice thickness and height of the ice sheet. And it sends that information back to the land model, which can adjust the precipitation based on the height of the ice sheet. So it will give, a different melt profile based on the altitude of the ice sheet at that point. However, the atmosphere is not updated. The atmosphere starts its run with a certain topography and it finishes its run with that topography. It doesn't see a change. So there's always been this sort of weird little space between the bottom of the atmosphere and the surface of the land. And there's been some debate in CSM about who owns that particular air in different places. And this is definitely a gray area. So what we do is every 10 years or so, we have to regenerate those files for the atmosphere and update it. Or just assume that the ice sheet isn't changing too much in, say, a PI simulation or a current day simulation to cause a lot of issues with the atmosphere. But this is definitely a problem that we'd like to fix going forward.
Good. Sounds good. Thank you.
Mhm.
All right, thank you. We're going to continue, and our next speaker is Kishwan Kang, who is going to continue this Solidus topic and talking about exact restart in Sitcom SVE. Can you present your talk yourself, Kishwan?
Yes.
Awesome.
Sorry. Can you see my screen now?
Yes.
Okay. Yes. Yeah. Again, I think I follow up Kate's talks and the general background of the GIA model Kate gave, and it makes my talk really easy. So in my talk, I will just introduce the implementation of the restart option in current Sitcom SVE. And some background right now, I think there are many existing studies to coupling the ice sheet model and GIA procedures. And I show here two main group. So this is one of the first, I think the first group in the world, in Gomez group, they developed this coupling procedures as I showed here. And among the different groups, I think the coupling procedures are quite different based on how the physics processes in their ice model and how the geophysics process in GIA model, and also when they exchange the input file between the ice model and GIA model. So this is basically the differences in different studies. And here I want to really focus on the third one. So just when we start to exchange the input between ice and GIA, right now, Gomez, as I showed here, they run the ice model, and then they run the ice model independently, and then they give the ice thickness history, I think, from the beginning and until the end, and then just exchange this ice thickness model with GIA model, and then just run the GIA model through the whole entire time period. So in this way, their model, they only exchange the input between these two model at the end of the entire computational time. and another group from the Delft University of Technology. In their group, they I think they split this couple iterative procedure into some like the time window more shorter. So as I showed here from Kaus's recent study, they coupled iSheet and GIA model during their kind of the coupling time step. So in this way, these two models, they exchange the input files in a shorter time window. For example, they run the ICE model for their defined coupling time step, this one time step, and then they start to exchange the ICE thickness with GIA model, and then just run GIA model and update the bedrock topography and the feedback to ICE model, and then do this iterative loop multiple times. After they get a convergent solution to both ICE and the topography, and then they move forward to next time step. It's hard to compare between these two methods. I think it really depends on how quickly the physics in ICE and GIA, they vary with time. So this depends on so many factors. For GIA, for example, if we have a softer Earth, those feedback would occur more fast, more rapid. So maybe the second method will give us a more curious results. But if the process, the physics process is just very, very slowly and stable through the whole entire time period, simulation period, maybe Gomez method is more straightforward procedure to use. And right now the Sitcom SVE, I think the workflow is more like what Gomez model. We can only just when the computation starts, they cannot pause they cannot pause and stop, and they need to just go to the last step. And right now I try to add the restart option in the Sitcom SVE, and the motivation, I think, it's very, very straightforward. With the restart, we can handle in long running simulations, even for the GIA model itself. For example, right now, when I use 3D GIA case with a higher spatial and temporal resolution, and the computational time will be just longer, sometimes longer than 24 hours, which would be just if you submit to the supercomputer, if there's more time limitations, that would cause some problem and waste the resources. And another big thing, I think it's really benefit to the coupled GIA and iSheet model is this restart option can enable us to adjust the parameters and the input file. For example, the ice thickness file during the computation time. And the strategies I used here is, I think it's also very straightforward. For the restart means we need to save the entire Earth state from the previous time step, and the equation here I gave is the May momentum equation, the weak form of the finite element analysis for the momentum equations we used in our GIA model. So different group, they include different geophysics processes here. I think in Sitcom SVE, we include all of the classic geophysics in GIA. For example, I showed here the first, the left side is the unknown parameters, unknowing variables, and the right side is the force. So for the left side, the first term is the classical stiffness matrix, I think, method they used. But for the GIA, we also include another additional two terms, the second and the third. You can say it's related to the little g, which is caused by the self-gravitational effects were included in our governing equations. Some group like the second method I mentioned before, they ignore the second and third terms, and so due to we include the self-gravitational, also the compressibility of the material. For the fourth part, we have multiple additional force from the density discontinuity profiles, also through all the material body besides the surface load. So all of those complexity make the Earth state it's more complicated than the other group. So I gave another summary. For example, this is a matrix form we need to solve by our GIA solver, and the stiffness matrix K, as I showed before, will depends on the Lamé parameters, viscosities, also the gravitational related terms, and the V here is the unknown variables, the incremental displacement at each node we need to solve by our solver. And on the right side, you can see there are two terms, and we have the incremental force term, which depend on the incremental gravitational potential, and you can see this gravitational potential, which in turn depends on the unknowing displacement V. So we need additional iteration to solve this equation. And another term, I think it's important to the restart option, is the F0. We call this initial force. This will include the pre-stress, the accumulated load, topography, geopotential, and the polar water. All of this depends on the state from the previous time step. And here I gave the overview of the workflow in Sitcom SVE now, and how I end the restart options based on this workflow. So you can say this is a stage I in the Sitcom SVE. So you can say we need initialization first, initialization for all of those variables. And then, for example, we have the ice thickness at epoch Ti, and we need to, we just set the time interval at this stage, at this particular stage for the ice thickness, and then we assemble stiffness matrix for this one particular stage, and then we load the ice thickness at this two time step, the before and current, and then calculate the incremental ice thickness change, and based on this incremental ice thickness change, we can calculate further the static ocean load. This will include the evolution of the ocean mass, also the load-induced gravitational geopotential. And another part we need to rate the state, but multiple state from the previous time step. For example, the pre-stress, the accumulated topography, accumulated gravitational potential, and the dynamic ocean load, also the polar water. And all of this we read from the global variables in current sitcom SVE. And after we have this initial force and incremental force, and we can initial force, and we can solve this equation and get the updated incremental displacement way. As I mentioned, there's another fourth term depends on this incremental displacement field. So we update the initial incremental force, and then just do the iteration multiple times to have a converged solution for V. And after we got a good solution for incremental displacement V, and then we use this to update those state from previous step, and then we can just use those state to go to next stage. And right now I just split here, and then before we save all of those through the static, either static variables or the global array of variables. Right now I just save all of those field, the accumulated field into the checkpoint file for the current step, and then use this checkpoint. And then for the next step, I can load those checkpoints to restart the calculation. And another thing, if I do after I have this checkpoint options, and then we can say from this part, before we use the predefined ice thickness, even though we need to read in only two epochs of the ice thickness history, but we need prepare all of those ice thickness history before our calculations and load it at particular stage. After we have this restart options, and then here I think we can just update our thickness, for example, from CSAM in the future, and go this iteration.
Hey, Keshwan, two more minutes.
Yeah, good. This is actually the last page. So the issues to be solved right now is I have this restart option, but when I need to benchmark against the original SVE solution to make sure all of those state I saved in the checkpoint correctly. And another step is maybe with Kate or Shijie's help, we can just replace the pre-refined ice thickness with with system output, and when we design the iteration loop over this one entire coupling time step to seek convergent solutions for incremental displacement in GIM model, also the ice thickness change in CSAM. So I'm ready to take any questions. So this is my end of the talk. Thank you so much for your time.
And we have time for one question maybe for Keshwan. Nobody? All right, let's move on then for our last talk of this first segment. Our next talk is on mountain glaciers, and Summer Minara is going to present it.
All right, hello everyone. So some of you are perhaps already familiar with this work. This is on glaciers using the ice sheet model. We have
Great, full presentation mode, please.
And we have presented on this before, but today I'll just give a very quick review of the things that we have done. What are the next steps? But more importantly, we want to get feedback from the CISM user community in terms of your interest and whether you want to use this new development. So I want to start off by defining glaciers, and we define glaciers as per the Randolph Glacier Inventory. So everything that is assigned a glacier ID in RGI is a glacier to us. Everything else is ice cap or ice sheet. And there are two broad categories here. So polar glaciers and mountain glaciers. These are very different in terms of their sizes and shapes, and they're studied for different reasons. Polar glaciers are very important in terms of sea level rise. Mountain glaciers are very important in terms of regional water resources. And we want to simulate all of these different types of glaciers. So the figure on the left is showing the largest glacier. This one in light blue outline. This is as per RGI version 6. And its area is over 7,500 square kilometer. And the figure on the right side is showing a few glaciers in the Karakoram region. So this one at the top is Siachen, and this is the largest outside the polar regions in terms of area. So it's a little over 1,000 square kilometer. But you can also see that its surface geometry is quite complex. It has a number of these tributaries, and this is something I'm going to come back to later. There are a few glaciers that are mid-size, and then most of the glaciers in mountainous regions are these type. They're very small, so they would be under a kilometer in their longest direction. And right from the beginning, you can understand that this would be very complicated to simulate in an ice sheet model because we have these glaciers in all shapes and sizes. There is spatial discontinuity in ice cover. So unlike ice sheets, we need to account for all of these different characteristics. And we have to be very careful when we are creating input data and domain file, but also looking at what resolution we want to run this model at. So we did our first, hold on. We did our first simulations in the European Alps region, and the reason was that there is some more observational data here that we can use to constrain our model. So this region that I'm showing in the map, all these blue colors are around 3,900 glaciers. And the largest one here is LH, and I'm showing its thickness distribution. So it's more than 500 meters in some regions. But most of the glaciers here are less than a kilometer square in area. And many of the smaller ones are under 10,000 square meters. So again, you can see the differences in the scale and the shapes here. And in this case, we went with a 100-meter grid resolution so that we can account for all of these different types of glaciers. And this is pretty much as fine as you can go with such models. Our DEM resolution was 90 meter, and below that, there is no further information. So this is very high resolution runs using an ice sheet model. So I'm not going to go into the details of the schemes and our setup. It's a very quick summary. As an ice sheet model, CISM does not compute mass balance. But for mountain glaciers, we introduced a simple temperature index scheme. And here the mass balance is a function of precipitation and temperature. And we have these two parameters, alpha and mu, which we tune for each glacier. So alpha is the precipitation correction factor, and mu is the more important one. This is the temperature sensitivity parameter. It is also known as the degree day factor, and we have one value across the entire glacier. For ice dynamics, we use the DEVA scheme. So this is depth integrated viscosity approximation. And here we had another parameter, CP. This is the friction coefficient. And during our spin up, which we did for 10,000 years, we try to nudge this friction coefficient to meet a target thickness that we provide as an input in our model. I'm going to jump into some of the results so that you can get a sense of what type of simulations we did with CISM. This is a comparison of the simulated thickness from CISM, and we are comparing it with this dataset Grab et al. This was an aerial survey that was done during 2016 and 2020, and they use ground penetrating radar to determine the glacier thickness in these regions. It's always tricky to compare model output with observations. They're not always similar. In this case, the glacier outlines were very different. But the more important thing here was that we wanted to see whether the magnitudes and the spatial pattern as simulated by CISM were comparable to observations. And you can see that CISM performs extremely well here in terms of the spatial patterns of thickness distribution and also magnitudes for some of the smaller glaciers that you can see here. So we were very happy with these results. And of course, this is pretty much the first time we are doing these simulations with CISM. So we also did comparisons for velocities. Here I'm showing some of the largest glaciers in the Alps region. And I'm showing the surface velocity here. The bottom two panel are the difference between the CISM velocities and two satellite-derived velocity products. I will skip the details here. The reason why we looked at these larger glaciers was because these are the thicker ones. And this is where we were seeing the most or the largest differences between those satellite-based products. For example, you can see that in some regions, CISM is overestimating. Those are the green colors, and those are usually either in the glacier tongues or in some of the accumulation zones. In other cases, it is underestimating, especially at higher elevations. And there, I mean, we can go into detail here, but velocity is not a target variable. We were trying to match the thickness with observations. And these velocity differences are because of differences in our thickness output. And so there are some details here that we need to parse out even further. So some of the results here, this is committed glacier area and volume loss as simulated by CISM in the top panel. So on the left side is the thickness profile of these glaciers in 2003, and this is the RGI state. On the right side is the committed loss. So committed loss here means that if the present day climate was to continue for another couple of 100 years without any further changes, how are these glaciers going to behave? And you can see that there is going to be a massive loss in both area and volume. Of course, these are simulated results. Some of the smaller glaciers are going to disappear. Some of the mid-sized glaciers are going to break down into smaller glaciers. And then, of course, we are seeing a reduction in thickness as well. And these results are quite similar to what we see in literature. So nearly all the models are simulating similar patterns. This is one study in 2019. Their observed state and present day climate was slightly different, but again, pretty much the results are quite similar. And finally, this was the first time that CISM participated in Glacier MEP, so the third phase of Glacier MEP. This was the first time that any ice sheet model or these type of distributed models participated in this activity. So this is just one of the results there. What we are showing here at the x-axis is the simulation year for different models that are shown in these different colors here, and the y-axis is showing the volume change. So these are two time slices, 1995 to 2014, which was the present day in CMIP6, and a green future scenario, end of century, using one of the climate forcing model. There are differences in magnitude, so you can see a spread across the models, but the sign of change is consistent. All the models are simulating a loss in these glacier, their volume, both with present day climate and even with the green future scenario. So CISM is in brown color here, and I'm going to come back to this spread across the models. But if you're interested in more details for either the CISM work or the Glacier MEP3 results, both of these papers are under review now, but their preprints are available. So all the details from CISM are in GMD. I think it is posted now, or it would be sometime this week. So you can just go there and provide your feedback. And the Glacier MEP manuscript is available as well online. So now moving on to what we are thinking about, what are the ongoing work. I already mentioned that within Glacier MEP3, there were 6 models that submitted their results for Alps, and there was a great deal of spread across those models. This is using another of forcing from IPSL, and you can see that the spread is even larger here. So the question is, with CISM, of course, we have some improvements in process representation. It is a more complex model, but does this mean that we are going to get better results? And even a bigger question is, what do we mean by better results? And why are these differences across models? Can we try to understand these even further? So there are 3 categories that we want to look into to understand these model differences. The first is the mass balance or mass balance scheme. Second is how the geometry is represented in these models, and then what ice flow solver we are using. So for the first one, mass balance, I mentioned earlier that we introduced a simple mass balance scheme where we just had this one, where we had mu, which was consistent across the glacier area. But in reality, these glaciers have very different elevation classes, slopes, and aspect. So just to give an example, these are the 10 largest glaciers in the Karakoram region. If you just look at Patura, you can see that its snout is at elevation less than 3,000 meters. And some of the tributaries at the higher elevation are over 7,000 meters. So even within the span of this one small glacier is elevation difference of 4,000 meters. And this is very important for mass balance computations. If you look at slope and aspect, so these are a cluster of small glacier in the Alps. I forgot to put a scale bar here, but these are some of the smaller glaciers. So on the right side, this is showing the aspect profile for these glaciers. If we just look at this one, it is shaped like a valley. So this side is facing northwest. This side is facing southeast to southwest. So the amount of solar radiation they're going to be receiving is going to be different, and that is also going to affect the mass balance computations. And same with slope. So some regions are steeper as compared to others. So right now we are doing some work with the community land model, or CTSM, as Kate mentioned. It has a configuration called hill slope hydrology. It is quite similar to the FATES configuration, and this hill slope hydrology can account for all of these differences in elevation classes and slope and aspect. And then we are going to use that to get energy-based scheme for the mass balance. Some of other things that we are discussing, and this is a little trickier in terms of, again, why these models are different. Some of the glacier models right now are called these flow line models. So they would create a flow line across the valley of these glaciers, and then they cut cross sections, and across these cross sections, they compute the mass fluxes and the velocities. Whereas CISM is this distributed model with 3-dimensional geometry. So we are trying to also figure out how we can understand the effect of these differences on geometry evolution changes in these models. So I'm going to end here. Again, the more important element was to understand and to gauge the interest in this community. And I've just given 4 classifications here in terms of model development and improvements. For example, for frontal ablation or maybe surges, in terms of different domains, in terms of science applications, and also in terms of how we can improve the usability and documentation. So I'm going to end here. If there are further questions, Bill did all the model development here. So if you have any serious questions about that, he's the person to reach out to.
Thank you. We have time for a question or two for Summer. Yeah, Sean?
Do you have a seasonal variation of the glaciers so you can use to benchmark model?
No. So we provide monthly data, but our outputs right now are all annual. We set up the model for Glacier MEP3 simulations, which were these centurial scale and millennial scale assessments. But with the new work with CTSM hill slope hydrology, actually we are going to sub-seasonal scales for mass balance assessments, because that has a great deal of significance for hydrology, and that's a science application aspect. But right now we don't have seasonal differences in geometry changes in terms of area and volume.
A very quick follow-up. Do you have observation?
Oh, seasonal observations. So no, the thickness data that we have are annual averages. In fact, they're averages over long time periods. Same with the velocities. Those are the swatches from the satellite, so they're at specific times. So we don't have a continuous time series at monthly time scales of most of these variables.
Thanks. Dave, go ahead.
Yeah, thanks. Looks like a really nice data set. I was just wondering, at least for the alpine glaciers, I think there's a few glaciers in the Alps which have quite good thickness data sets from GPR. Probably not many at 100 meters resolution. And I guess most of them have very little data, or maybe some don't have any data at all for thickness. So how do you get around that when you're coming up with your 100 meters model?
Sorry, I missed the second part. So we do have better observation for alpine glaciers, and this is one of those data sets, but I missed the middle part.
Yeah, I was wondering, I think there's probably quite good bedrock data sets for some glaciers in the Alps, but presumably a lot of glaciers in the Alps still have very few or very sparse thickness observations. So I was wondering do you have to do some interpolation or some sort of best
No.
guess? Or
I see. So we were providing this graph data that you're seeing on the slide right now. This is an independent data that we didn't provide as an input to the model. So the input thickness was coming from this Farinoti study. What they did was use 5 different models to create an estimate of the glacier thickness.
Okay.
Those were not even observations. Those were actually model outputs combined together to produce this distributed thickness profile. So we did not have to do any interpolation. We just had to do regridding to our model grid, but we didn't do any. There wasn't any missing data in that data set.
Okay.
Same with this, the one that you're seeing on slide right now. So Grab et al. In their study, they did all the work to produce these spatial profiles of the glaciers, and we didn't do any cleanup or regridding here.
Okay, thanks.
All right. So it is 10 a.m. We're going to break for 20 minutes, and we convene at 10:20. So yeah, we'll start 5 minutes late, but that's it. Okay. Thank you, everybody. Thanks again for all the speakers this morning. Hey.
You opportunity to package you and like thought that maybe a little bit bigger, but it's not.
No, yeah, I think it's fine. It's nice to be able to see people when they raise their hands.
Yeah.
I was thinking that might be
Thank
good.
you for your presentation. Now that I know, like,
It's not the biggest issue in the world at all.
If you want to design any projects,
yeah,
now you're trying to make
yeah. I know we had talked about trying to model Surge Glacier, but I don't think that's a project to start with, you know.
Surge is the most tricky
Right.
component because then you would have to go to smaller time scales.
Right.
And even with satellite velocity observation, it's really tricky for satellite to capture the
Good, but then also like.
and we have much information, much data to really be able to train our models. So that's probably one of the most challenging components, but we were talking that at some point we have to
Yes.
get
Yeah.
into that.
Yeah, I'm sure. Yeah.
Yeah,
Really mostly used that thick
Okay, so I'm going to start my scripts again. Welcome back, everyone. We're going to go into our second part of this morning session, and our next speaker is supposed to be Heiko Golzer, but I do not know if he's here. I don't see him. Okay, then I guess
Gunther, I'll send him a text. I can also switch with him if you want.
we could do that. That would be if you could send him a text and switch with him. That would be great. Or we can have Tim go first. But if you want to go first, Michael, go ahead.
So I just sent him a text, and then maybe I start. Well, let's
do that. That sounds great. Thank you.
Yeah, no problem. Am I supposed to share my slides or?
Yes, I didn't receive your slides, so we don't have your slides.
I've put them in the folder.
Oh, you have.
Yeah, I was a bit late. Sorry about that. Still, I share mine, or you open them?
You're happy to share yours. You're more than welcome to share yours.
Okay, cool. All right. Okay. So can you see the slides?
Yes, awesome.
Okay, full screen, right?
Yes. Well, I can see your.
Oh, the bar. Yeah. Okay, now it's good.
Okay,
Okay,
awesome.
thanks.
Okay, thank you.
I'm gonna give an overview on our work with the Norwegian Earth System Model, NORIESM, in coupling an Antarctic ice sheet component. So this work is clearly from the co-authors. You see a collaboration between Norway and the US, and it is made possible, all this work, by the huge amount of work by Mariana Wertenstein at the Meteorological Office in Norway. So I'm gonna start with the overall goals, which are quite simple in some sense. So this is what's going on in the second version, so the latest published version of the Norwegian Earth System Model, NORIESM 2. So it's a model that has many shared components with the Community Earth System Model, and the sea ice, the land component, and the atmosphere, even though there is a different module for aerosols. And then we have MOSART for the runoff, and then we have a different ocean model, BLOM, and biogeochemistry, HIMOC. For the ice sheet model component, we also have a CISM, and the second version of NORIESM, as the second version of CSM, included a Greenland ice sheet component. And you can see in the illustration a bit the main communication between CISM and other model components. So CLM would send every year surface mass balance to CISM over Greenland, and will then send back to CAM elevation changes and albedo changes to CLM, and freshwater fluxes to the ocean component, BLOM. What is really missing here in the second version of NORIESM is the ocean forcing. So now that we are working towards next version, NORIESM 2.5, and also later versions, basically what we want to have is have also a dynamic Antarctic ice sheet component, so to have both ice sheets in the model, and then also including some form of ocean forcing from the ocean model to CISM. And that's pretty much what I'm gonna talk about. The idea, of course, is that we want to in some way represent this system, right, in Antarctica, with the melting under the ice shelves and the release of meltwater, which can contribute to the formation of dense shelf water that then fall to the bottom, forming Antarctic bottom water, and the interaction with also sea ice formation and polynya and katabatic winds and all. So it's a very complex system, and of course, it's going to be very complicated to really represent that in an Earth system model, but that's what we are going to try. And also to somehow represent the ocean forcing in the marine terminating fjords in Greenland. So for that, it may be a bit less clear for the moment how we will proceed, but in principle, we would very much like to include some form of ocean forcing for Greenland as well. So now the good news is that the coupling is working, and we started to run some technical tests, and with both IceSheets on in NORI-SM, and that's what I'm gonna show you. Of course, here we don't have a fully spun up or even tuned climate. So this whatever I'm showing you is very much like a conceptual sort of a result to show what we have and that the model is working. You can see here on the left our NORI-SM simulated SMB over Greenland. I've put the latest version of RACMO. I think it's the latest, RACMO 2.4. Just as a comparison, we knew already that the SMB from CLM is quite good in the western part of Greenland for the ablation area, and we have instead of a bit of a problem in the east with the precipitation because there is no downscaling for that. So this is how the SMB at the moment is looking like, and let's say nothing too new from NORI-SM 2 in this case. And now this is what the SMB is looking like over Antarctica. So we have basically no ablation except from some very few points in the Antarctic Peninsula. And then we have, of course, the accumulation. And we can see that maybe, again, comparing that to RACMO, maybe we can be slightly pleased with the fact that the interior of Antarctica is quite dry. But then you can see how we fail at the moment to catch the precipitation patterns. And I mean, there is, of course, some resemblance, but then there is the big problem of passing from the 1 degree to the 8 kilometers, in this case, 8 kilometers grid, and not having a distribution of precipitation that accounts for orography, for instance, or like in some way to the high resolution topography. Now coming to the ocean, what are we doing about it in Antarctica? What is happening at the moment is that we are sending from the ocean model BLOM ocean temperature and salinity at multiple levels, 30 levels between the subsurface and about 2,000 meters depth. We're sending this ocean temperature and salinity 3D fields from BLOM to CISM. Now the point is that BLOM as an ocean model is not resolving the cavities. So we're basically sending some far field fields. And you can see an example here of what a remap field is looking like. So you see that there is all this white around Antarctica, which is basically missing values because we don't have values for that. So then what's happening is that we're using an extrapolation algorithm inside CISM, and this was developed by Bill Lipscomb, to basically push the ocean properties, ocean column properties inside the edge of cavities until the very interface between the ice sheet and the ocean. Then what we are doing at the moment is that we are using these extrapolated fields to compute basal melting using the standard ISMIP6 two-equation parameterization that was used for Antarctica. And this is basically relating the basal melt to the ocean thermal forcing, which is this orange term here that is a quadratic dependence. And this is basically the difference between the ocean temperature at a given depth and the freezing point of ocean water at given depth and salinity. You see, this is the dependence on depth and salinity. Of course, this is a semi-empirical parameterization. We have no cavity circulation, even in a form of a plume model. So this is very much simplified in a way, but that's also, on the other hand, state of the art from what regards like ISMIP and ICID modeling in general. This is what the basal melt, the substrate melting in Antarctica is looking like in our fully coupled tests, in our first fully coupled test. And well, there isn't really too much to say at the moment, except that we sort of have higher melting in West Antarctica and lower values in big ice shelves like the Ross and the Filtron, and also a bit in the east. And these somehow make sense in a way, but again, we need to see what happens then with a fully spun up climate and also what the feedbacks are doing to the ocean circulation. Now, one point that is important, I think, to touch, even though it's a bit technical, is that you could see, maybe you didn't notice, but you can see in these large basins, you can see these sort of striped patterns, and these are basically because of the extrapolation algorithm, which is essentially pushing the ocean properties horizontally until, except if there is a sill, for instance, or some bedrock bump that is preventing the water to fill in. And so when there is no full accessibility, the extrapolation is also done vertically. So there is a little bit of a mix of horizontal extrapolation and vertical extrapolation, depending on the bedrock topography. And this is in principle working nice over like sort of narrow cavities. But then when we have like big cavities like the Ross or the Fusel-Ron, then there is where there is actually lateral circulation, then we get this stripe pattern and we need to do something a bit better. And what we did so far is that we included Gaussian smoothing in the algorithm. At the moment, this is done at the end of the algorithm, but maybe could be a good idea to do it like in the very first, in the very beginning of the extrapolation process. But you can see basically how before and after the smoothing, the forcing fields are looking like. This is the same year, same simulations, just applying or not. I mean, not applying and then applying the smoothing on the right. And you can see that, I mean, it is working decently, let's put it like that. Even though we need to do a lot of testing on the level of smoothing, and we need to do a bit of a comparison also with the observation to really say that we're pleased and we can go on. Another attempt that we would like to explore is that maybe use more advanced methods to calculate subshell melting, and that's, for instance, using some form of plume model like Pico or LADDI or the AI-based MeltNet. And you can see an example here on the right. This figure here is an example of a LADDI offline run that was forced with this 3D NORIES motion data. And I mean, clearly, of course, especially in the large cavities, we get a bit more the pattern of the more melt close to the grounding line, and also depending on the lateral circulation of the meltwater plume. Another important aspect that we would like to really consider is attempting to inject the meltwater from the cavities or from subshell melting, not at the surface layers, which is done at the moment, but at the depth of formation, or at least spread it over some representative depth between the surface and maybe 400 meters or 800 meters. We really need to do some testing there, and it's not easy, but we would really like to include this modification in the code. Now, before concluding, the next steps towards CMIP 7 and ISMIP 7. So now we are, as I said, we will keep testing and at some point making a choice on the ocean extrapolation scheme and on the parameterization for subshelf melting in Antarctica. And then we also need, as I said at the beginning, to do something about Greenland. So maybe we're collaborating with Heiko and Donald later to include a new parameterization for ocean melt at Greenland's more intermediate margins, even though at the moment it's not really clear what we can do. And then this is a little bit possible tentative roadmap of what's going to happen towards CMIP 7. So at the moment, there is an ongoing spin-up with NORIES M2.5 without ice sheets on, climate only. Well, it is actually Earth system model only, because it's not only climate. And when this run at some point is maybe fairly close to equilibrium, we would like to take output and do some offline forcing for Greenland and Antarctica to start to see where the ice sheets, what the ice sheets want to do with this forcing. And we're going to probably exploit a lot, not only standalone season, but also this semi-coupled T-COMSAT mode. And then from that, starting an offline spin-up using the inversion technique to basically initialize the ice sheets. And we will also need to calibrate the ocean melt parameterizations. And the goal is that at some point we can turn on ice sheets in a fully coupled mode in RSM and basically have our own spin up, and then basically ending up with the DEC ISMIP7 experiments, couple experiments for ISMIP7. And at the moment, there is also the chance that for ISMIP7, we are going to include a dynamic Greenland. So there could be a little bit of exchange between these basically lines of work, but it's also a bit hard to say before really seeing what the climate forcing is looking like for Greenland and so on. And with this, I will conclude, and happy to take questions. Thanks.
Thank you, Michele. We have time for questions. Yeah, go ahead, Rachel.
So McKay, if you implemented the subshelf melting like plume model, what differences do you think you would maybe see from how you're currently estimating meltwater in those larger basins?
Yeah, I mean, I think that this figure here with LAD is a good example of what could be different. So, in principle, we would expect, at least for the melting, more melt, basically a higher gradient of melt as you get closer to the grounding line, so higher and higher melt, and less so when you're like far away from the grounding line, with possibly some refreezing, which the two equation at the moment is really not doing at all. And then in terms of freshwater forcing, I mean, of course, this could change the overall budget, of course, of a whole basin. And so the like overall quantity of freshwater that you would put in the ocean would be different. Then I think it really depends how you would implement the freshwater forcing, because I guess maybe if there is like a spatial difference, but the overall like basin number is the same, then maybe for how things are done at the moment, maybe there wouldn't be much of a difference. But then, of course, if we start to inject meltwater at depth, then there could be also difference in that respect, because maybe at higher depths, close to the grounding line, you would start to have more fresh water and less maybe close to the ice shelf edge.
Thank you. That's very interesting.
Awesome. Any other questions for Michele? Thank you so much, Michele, for a great
Thanks.
talk.
Yeah.
So I don't see Heiko online, so we're going to continue. Obviously, we're going to here for now. So our next speaker is going to be Kim van der Akker about force-free transatlantic simulation with little extras that are unspecified, but he's going to tell us all about it. Are you here, Tim? I can see your picture.
Yes, I'm here. I'm
Yeah,
just
all right.
setting up the. Let me see. I want to share my. There we go. So, can you see a presentation right now?
It's coming.
Can you see it?
Nope.
No.
Ah, crap.
The stop presenting button.
I'll try. We try it like this. It's visible now.
Yes.
Yeah. All right. So actually, I'm realizing now that I put the spoiler already on the screen here. That's so the little extras that are unspecified in the title of the presentation is going to be about calving. So I'm going to be talking about ocean force Antarctic ice sheet simulations, and I will start the talk with presenting some results on whether or not to include your present-day mass change rates, your present-day disequilibrium of the Antarctic ice sheet system, and if it actually matters on runs where you're at forcing, ocean forcing. And then we're going to slowly move on to other ocean forcing in the form of calving. For this, I work together with Bill and Gunther and Willem-Jan Roderick from the Utrecht University. So modeling content system, of course, I'm using SISM. I'm using the depth integrated viscosity approximation. I am modeling the whole Antarctic ice sheet, and we will, of course, take a look at the whole of the ice sheet with the results. But I focus a little bit more on the Amundsen Sea region because that's the area where interesting stuff is happening right now. I'm using a Zoot-Iverson sliding law, tuning the friction parameters and ocean temperature perturbations. I'm using the same mesomelt parameterization as Michele just showed us, including the same interpolation methods. And I based my versional thickness. I don't include velocities. Generally, the ice sheet velocities that I model are, I would say, they get like a 6 in Dutch grading system, which means that you have 60% on your grade if you give a student a grade on the test. They're all right. They're not perfect, but they're, yeah. And especially if you don't invert for them, they turn out to be very good actually. So that's the context. So what I've showed you before is this kind of plots, where on the left you can see the observed mass change rates from Smith et al. In 2020. I think you use ISET1 and ISET2 to calculate those. They're GIA and SME corrected. And on the right you can see what happens if you give those mass change rates to CISM and let it run for, in this case what you see is about 1,000 years, but typically Western Antarctic ice sheet collapse starts to happen at about 500 years. So this was a lot of the work that I've been doing for the last year was about this, including these mass change rates. And everything that I've done so far was with unforced simulation, so without any climate change or ocean warming. And that's, of course, the first question that you get if you talk to people about it. Okay, but what if you add forcing to these kind of simulation? What would happen then? So that's what we're going to do. Also, to kind of like to answer this intuitive question of like, if you add a lot of oceanic heat into your simulation, does it actually matter what you do for your initial states? Or is it just going to be forcing dominated anyway? So why bother? So we add ocean thermal forcing from 7 Earth system models from the CMIP6 ensemble. They're also used in ISMIP6, by the way. These are 4 runs with RCP or SSP 585 and 3 runs with 126. And we initialize the ice sheet with or without the observed mass change rates to see if it actually matters. And what you're seeing right here is a typical dead time average forcing of UKESM RCP 585. And you can actually see that there's a lot of warm water intrusion actually already happening at in the Amundsen Sea region, but also the Ross Shelf is pretty warm. And we're going to see what's the effect of that in a little bit, because here's a movie and it's running forward already. So we're now in the year 2100. You're seeing the thickness difference with respect to present day, and boom, Ross goes. And there we go, Field and goes as well. And now, only now, the Amundsen Sea starts to break out of all of its floating ice. So this is a very, I mean, UKESM predicts a lot of warming in the Southern Ocean, and it's of course RCP 585. But the main idea that I want to give you from this simulation is, well, if we run into the future with forcing, with CISM, then the Western Arctic ice sheet isn't our biggest problem, to put it mildly. So this is of course like a very strong case. But anyway, so if you're just going to focus on the Amundsen Sea region, for example, you're interested in the Western Arctic ice sheet collapse as I was before, they can make graphs that looks like this. So on the bottom right you see a spaghetti plot, as I call them, with on the y-axis is typical something like ice volume above flotation. In this case, on the left, you see global mean sea level rise. And on the right, you see the ice volume above flotation percentage change on the Western Arctic ice sheet over time. And every blue dashed line is not initialized with the HCT, or the mass change rates. And every red solid line is actually initialized with the observed mass change rates. And every marker corresponds to the same Earth system model forcing that we used. And in all cases, initializing your ice sheet with the HCT will speed up the collapse and get you more sea level rise sooner compared to the case where you don't initialize your ice sheet model with the HCT. And actually, because the spread in this figure is pretty big, so especially for the 2.6 cases, like the effect of initializing your ice sheet model with the HCT is larger for when you're applying a little bit of forcing, so 2.6 compared to 585 scenarios where you just apply a lot of forcing. But still, I would say if you're just doing a Western Arctic ice sheet collapse, it's probably good to include the DHCT, the present day equilibrium, in your run, because it matters a lot for your 2x collapse. So the thing is that if you're then looking at the Antarctic ice sheet as a whole, it doesn't really matter. Like it doesn't really matter. It doesn't matter. It does matter more for the 2.6 cases again. So you can clearly in this case see this graph is for the whole Antarctic ice sheet, by the way. You can clearly see that there is like two kind of tails happening. The top tail is the 2.6 scenarios again, and the bottom ones are again grouped together with the 5.5 scenarios. And the interesting thing here is basically there are two interesting things happening here. I think is that for the whole Antarctic ice sheet, it does not matter a lot if you're including the HCT in your simulation or not. And in some of the 5.5 cases, you can actually see that the red lines are above the blue lines. So at the end, like close to 500 years into the future, which should be 2,500, you can see that some of the red lines are predicting less sea level rise than their blue equivalents, which means that in the case that you're initializing with your DHCT, you get more or less sea level rise compared to the runs where you are not initializing with DHCT. And this is caused by, so if you might remember that there is in Queen Motland a little bit of thickening happening right now. So in these runs, typically the Western Antarctic ice sheet disintegrates anyway. Your field neuron and your Ross shelf disappear anyway. And then you're basically left with the East Antarctic ice sheet and some kind of peninsula with areas that are above sea level or resting on bedrock above sea level. And if you're applying the HCT in some of these areas on the East Antarctic ice sheet, there is still a thickening in the present day observation. That will continue according to these simulations. So that's kind of then I'm going to shift a little bit to another cool results that I have been working on recently. And we're going to talk about some stress-based calving, because the runs that you saw before, and although the big shelves disappeared, there was no real calving law or algorithm in the model at that point. We basically used a no advanced calving front. So as soon as you as soon as the ice sheet would advance to the observed present day calving front, it would be cut off right there and could not advance any further. It could retreat theoretically, but only if the ice would disappear completely. So get to a thickness of below a single meter. So Bill has been working does a quite cool work with this stress-based calving regime, where he basically parameterized the lateral calving rate C as the velocity of this grid cell times a fraction of stresses. So in the top of the fraction you can see a regular tau, which is the stress that you're calving from, and at the bottom there's a tau threshold, which is a stress threshold. And it basically tells us if your stress at the calving front goes above the threshold, your calving rate gets larger than your velocities. Therefore, your calving front will retreat inland. And the other way around, of course, if your stresses are above that. And the stresses that compute is just the principal horizontal stress of the, it's the horizontal stress tensor that we use for this, composed of the two eigenvalues of the stress tensor. So then me and Bill have been emailing a lot about this, and we typically send pictures like this, in which you can see it's mostly green, which is good. Yellow means that there is ice floating at that position where it shouldn't be floating. So it could either be that the calving front is too far or the grounding line is a little bit shifted. And blue spots mean that there is ice not floating or not present at all where it should be floating and or present. So you can vaguely see that this is Antarctica, and that's exactly the point, because what we're doing here is we're doing a free spin-up without no advanced calving, because we're actually applying stress-based calving here with a threshold of 85 kilopascals. And you can see that for most of the continent, actually, there is grid cells. There's a sparse amount of grid cells that are, that receive that have too much ice or too little ice, or floating or not. But in general, I would say, like with one single threshold value for the whole of the continent, you get the calving front that looks pretty good compared to observations. So now we're going to move to some preliminary results using this stress-based calving, because I mean, I have to say this is work that I've basically done yesterday, or I found the final results yesterday, and I noticed that I've been running on 2 different GitHub branches and did not always nicely rebuild SYSM in between, so there was a bit of chaos in these runs. Anyway, I've been able to do a forced run with NORI-ESN, where I'm applying the same strategy as that I did before. I initialized my ice sheet model with DHCT, without DHCT. And then the without DHCT run, I also did a stress-based calving continuation. That's what you can see right here. So the blue solid lines are always no advanced calving, so the old calving and no DHCT. The red lines are no advanced calving, but with DHCT. And the dashed lines are no DHT, but stress-based calving. And you can actually see here that for the Antarctic ice sheet muscles in its entirety, this makes quite a big difference. I think almost double the contribution that you get from just adding your mass change rates into your ice sheet modeling. And for the Amundsen Sea region, it's actually even more. Like your collapse of the Western Antarctic ice sheet happens way faster if you're applying this stress-based calving, and it's mainly caused by our culprit. This is the stress-based calving simulation, by the way, a little movie. You can see that there is actually no ice at all being built up as soon as thwaites start to collapse. The white means that there is no ice. It's basically there is no shelf at this point. So, and this is a typical thing that I noticed in these kind of simulations, that especially thwaites seems to be very vulnerable to this stress-based calving algorithm. And you'll usually end up with a case where there is no big, like where they typically found there was a big ice shelf forming here as soon as the grounding line starts to retreat very fast, but it basically disappears completely. So thwaites is very sensitive for this new parameterization. And these are, maybe I should skip these because these are very preliminary results. You can see that the runs are not even done yet. They end up at like 250 years. But the main idea again is that if you add stress-based calving to your no DHT runs, your ice sheet mass loss goes way faster. So that's kind of the two conclusions that I want to end with. The mass change rates, including in your initialization, matter if you're doing Western Antarctic ice sheet simulations or projections. And they matter less for the Eastern Antarctic ice sheet. So if you have to choose between focusing on the better Basel melt algorithm or adding DHT to your runs, I would probably choose the Basel melt ones. Stress-based calving leads to faster projected sea level rise, but that's preliminary, and I hope to get some more results out very soon. And with that, thank you for your attention, and I'm happy to take any questions.
Thank you, Tim. We have time for questions for Tim. Amy Kenny.
Hi, thanks. Very nice, Tim. One question. I mean, I have two questions, very small. One is about when you said that you use the extrapolation algorithm. Did you apply any smoothing to that, and or so did you have any of this stripe pattern? Is it something that you?
Yeah, you actually see the stripe pattern. I did the same thing as you did. I think I switched over it like pretty quickly and didn't go back to it to see like, oh, did you spot the lines in it? But yeah, there are lines in the. I showed this UKSM example, and you can clearly see the basin edges in the in this figure. So that's.
No, that's fine. I was just curious. And then the other question is, did you use the forcing from the ER system model like as it was, or did you apply any bias correction? You kept the bias correction that is already implemented in season. So did you do any like tuning, or you just said, okay, this is the forcing, let's see what happens? And
so. Oh, yeah, sorry, go ahead.
No, yeah, that's it. Yeah.
Yeah. So so what I did is during the inversion I inverted for the ocean temperature perturbations given the Jourdain data set, so the one from ISMIP 6, and then I rewrote my perturbations in such a way that you start, at least the DHT runs, that they start with the same kind of perturbation, or the sum of the thermal forcing and delta T would be the same. And then slowly your forcing starts to take over after, I think, 20 or 30 or 40 years. That I take the average of the first 20 years and subtract that from the DT values.
Okay. Interesting, man. So it's a polished forcing that is giving you the melt. Yeah.
I've also tried it without the polished forcing, and it's there's not a big difference.
Okay.
The only difference that you get is that in the start of your run you get like nice DHT values, which is what I've been trying to get like for a lot of time. So that was nice to see, but then on the bigger picture, not a big difference.
Yeah, thanks. Very cool.
Okay. Any other question for Tim? Yeah. Joanna?
Yeah. Tim, so cool. This might be kind of a half-baked question, but so how do you plan to kind of address the stress-based capping law and kind of balance it out with just the idea that like it's not going to have I feel like it's unlikely that that using the stress-based capping law does just like have this crazy runaway like disappearance of the continent, or like what is your next step, I guess, for balancing this capping algorithm?
That's a very good question, and I'm also looking to the other side of the table that you're sitting from.
Yeah.
Because the big genius about the stress-based calving is Bill. He implemented this and basically said to me, like, Tim, look at me, I got a cool GitHub branch that you can try out. And I was like super enthusiastic and started playing with it and got these results. But so to me, the main goal for me is to get a stable spin up where I apply this one. Where I can do a model drift experiment that doesn't run away immediately without adding forcing or without adding DHT. After that, so if I have a stable spin up without model drift that I can use for a future simulation, I would say that the breakup of Thwaites is I don't dare to say that it's it's an
Yeah,
outlier, I would say, but it's not completely unexpected in a sense. Like
No, I always forget that you do need a stable spin up in this world. So yeah, that makes
Yeah, you
sense.
do.
But very cool. It looks awesome.
I have one question for you, Tim. Like in the movie that you showed with the fast retreat of Thwaites, there's only retreat in the Amundsen Sea and nowhere else. Like, is it because the other sectors were not impacted by the parameterization, or it's because you only applied it in the Amundsen Sea?
No, I applied it on the whole continent. So theoretically, it could happen in the field neuron and the Ross as well. It just doesn't happen because, and that's the thing that I think is happening here, is that the basal melt is dominant in those areas. So
you applied both.
Okay. I also apply forcing in those scenarios. So what I found, and that's still preliminary. I'm not gonna. I cannot stress enough that this is very preliminary, but that I think that the basal melting is determining the fate of the Ross and the field neuron, and that the calving is going to determine the fate of the Amundsen Sea region. But that's the kind of thing where I think we're heading at.
Okay, awesome. Thanks a lot. We're moving on to our next speaker, Dave Chandler.
Okay. It's just
It's about Southern Ocean freshman hosing experiment.
Hey, can you see this and can you hear me okay?
Yeah.
It's a long way from Norway to the US, so hopefully I can shout. Yeah, so staying with Antarctica, I guess, or mostly. This talk is really more about land ice in the Earth system, and in particular the effects of fresh water on the Earth system, so fresh water from the ice sheets. And this is work I've been doing a lot with Petra Langebrock as part of the Ocean Ice project in the EU, and also collaboration with Heiko and Michaela in Bergen as well. So because of a question I was asked last week, which is what is a hosing experiment, I thought I'd put this slide in just in case you're not aware. So in Earth system modeling, a lot of Earth system models don't include an ice sheet, or they include an ice sheet in a very simple way. This is gradually changing, of course. So sometimes if you want to simulate the impacts of ice sheets on the Earth, on the climate, we can add water directly to the ocean to simulate extra melting. So even if we haven't got an ice sheet in the Earth system model, we can still add some fresh water into the system, see what happens to the climate if there's more melting. And it's a very crude way of doing it. We just add water as a boundary condition or a sort of forcing, and that's what's called a hosing experiment. They've been going on for sort of 10, 15 years. It's a fairly standard but crude method. So why might we want to do this? I think we can think about real world ice sheets and model world ice sheets, and I don't really need to explain a real world ice sheet to a room full of glaciologists. But the crucial part of this in an Earth system context is that we have this fresh water runoff from a real ice sheet, and this fresh water, or the freshwater fluxes into the ocean, can be from surface runoff if there's surface melt, or it can be from calving, which then calves icebergs that melt in the ocean somewhere, or it can be from basal melt beneath ice shelves. And there's two points here. First is the forcing of this fresh water. So the atmosphere is kind of forcing the surface runoff, whereas the ocean is forcing the basal melt. So if you have ocean warming or atmosphere warming, you could get increasing freshwater fluxes. And also the timescales. So if you have an increase in precipitation, for example, in the middle of the ice sheet, it takes hundreds of thousands of years for that kind of signal to propagate to the margins and increase the freshwater flux from the margin. But now if we have a model world ice sheet, and by model world I mean like a CMIP 6 type model, not SISM. This is just an Earth system model. Traditionally, ice sheets aren't included in these older Earth system models, or even a lot of the current ones. And so you just have a snow-covered mountain, which is got a fixed topography. If it snows in the middle of the ice sheet, you can't grow the ice sheet, so any excess snow is just sent straight to the ocean as a solid discharge into the ocean, so solid ice discharge, and it's spread across the coastal grid cells in some way. You can still have liquid runoff if the surface melting. But so comparing it with a real world ice sheet, the time scale is quite different. So if you have increasing precipitation in the middle of the ice sheet in this model world ice sheet, then that increase in precipitation is sent straight to the ocean directly. So there's no sort of delay of hundreds of thousands of years. And also the freshwater fluxes are only really driven by the atmosphere. So in this simple scheme, if the ocean gets warmer, it doesn't cause any more ice melting beneath the ice shelves, for example, because there aren't any ice shelves. So the ice, this kind of freshwater fluxes is only really sensitive to atmosphere changes. And so if you have this type of ice sheet in your Earth system model, then this is where hosing experiments are very, very useful. So I'm going to talk a bit more about what we've been doing in NORI-SM. And currently in our experiments, Greenland is a real world ice sheet, and this is using the coupling with SISM that Michaela was talking about already. So yeah, I don't need to explain any more about how that's done. In our version, then Antarctica still isn't coupled. So Antarctica is still like a snow-covered mountain. So if we want to simulate the effects of increasing basal melt, for example, from ice shelves, then we have to run hosing experiments. This is what we're doing, and the ultimate goal is to look at kind of interactions between the two ice sheets using these hosing experiments. And I did put this slide in just to compare very briefly differences between CSM2 and NORI-SM2. But again, because Michaela's already done this talk, he's already explained it. So there are lots of similarities between CSM2 and NORI-SM2. The main difference is being a different ocean model, really, from our point of view. So I'll not explain that anymore. So what are we doing? At the moment, we're running some pretty simple conceptualized experiments where we add fresh water to Antarctic coastal grid cells, and it's just added at the surface. So in the context of all of the hosing experiments that have been done by other people in the past, this is actually very simple. But it's following this SOFIA protocol, and SOFIA is a Southern Ocean freshwater input from Antarctica. It's a sort of informal community model into comparison at the moment, but it's going to become part of CMIP7, I think, or they're going to have some freshwater experiments in CMIP7. And in the simplest case, we're just adding 0.1 sieverts of freshwater evenly around the coast of Antarctica. So 0.1 sieverts is about 3,000 gigatons per year. And if you compare that with the current freshwater flux from Antarctica of about 2,000 gigatons per year, it's increasing it just by, well, 2.5 times or so. So it's quite a strong signal. Probably say something like by 2100 or so, it could be quite realistic. And where does this fit in with this Sophia project? There's a whole range of different experiments adding fresh water to. So the simplest one in tier 1 is this pre-industrial control and ant water, which is the one we're talking about here with the 0.1 sieverts. And then there's a whole bunch of more complicated or sort of less conceptual experiments further on in this project, which we may or may not do, not sure yet. And so far, we've just run 2 ensemble members for this tier 1 ant water experiment. One on a Norwegian computer called Betsy, and the other one on Derecho at NCAR. So I'm just going to talk about some very, very quick results. Well, yeah, I just had a really quick look at results from the Derecho runs. And again, I've only really had a chance to look at the very sort of broad scale outputs from these results. So in the left-hand plot here, I've just plotted the global mean SST, and then the blue line is the pre-industrial control. So this is without the freshwater forcing, but it does have coupled Greenland ice sheet, and that looks fairly stable over 140 years, which is good. In the orange line is the ant water experiment, where we've added 0.1 sieverts of fresh water around coastal Antarctica. And you can see then that causes a sort of gradual cooling in sea surface temperature averaged across the globe, which then stabilizes after about 50 or 60 years to be a little bit cooler than the pre-industrial control. And then I did start another little test where after 100 years, I turned off the freshwater forcing to see what would happen. So the forcing then reverts to pre-industrial. And it looks like the sea surface temperature is quite quickly heading back towards the pre-industrial control. So just from that short experiment, which didn't actually finish yet, it looks like the climate response is quite quickly reversible, at least in this experiment. And this cooling signal in SST is mainly caused by quite strong cooling in the southern ocean, and this is really a result that's common to all of these hazing experiments. And slightly weaker cooling in lower latitudes, and then there's still a response in the northern hemisphere as well. One of the things we do still have to do is to compare the magnitude of these responses with the variability. So we're not sure how many of these changes are statistically significant yet. That's probably the next task, I think. So yeah, not all of these anomalies might be statistically interesting, but that's the next job. Can also look at the sea ice thickness, and again, in the Southern Ocean, this is pretty standard response for these hosing experiments where we get a thicker sea ice, and that's because it's fresher. The surface layers are fresher, so it's easier to freeze it. But we also see a sea ice anomaly in the Arctic Ocean as well. And again, we have to look to see if this is a significant result or not. But it's quite interesting to get a response in the Northern Hemisphere if it is significant. Greenland ice sheet mass balance. So again, this is just the anomalies caused by adding fresh water in the Southern Ocean. So there's a bit of a negative SMB anomaly in the interior of Greenland, and I think that's because there's less precip. I'm not 100% sure yet. And then there's a positive anomaly around the margins, so there's less melting, I think. I haven't looked exactly at what the causes of this yet. So overall, this means that there's, I think, a little bit less surface runoff into the North Atlantic. So the effect of adding fresh water into the Southern Ocean is that you then get a bit less fresh water added into the North Atlantic, but it's only a very small difference. And looking at the Southern Ocean, there's a little bit less precipitation over Antarctica with in the Hosing experiment. And bearing in mind that Antarctica isn't coupled, so it's still a snow-covered mountain, if you get less precip over the continent, then you immediately get less fresh water fluxes into the Southern Ocean. So adding fresh water to the Southern Ocean then means that the response is you get a bit less added from the ice sheet. But if we look at the magnitudes of that change, then the reductions in liquid runoff and solid ice discharge from the snow capping scheme and the runoff scheme are very, very small in comparison with the forcing that we're applying. So it doesn't really make much difference overall. And actually, what's interesting in this plot is where if you look at the right hand map, this kind of red band around Antarctica shows you how the model is distributing the solid runoff across the ocean. So it's just in this very sort of narrow coastal strip that it's put in the solid runoff. So there's still a lot of work to do here. There's a lot of obviously a lot of data to look at even just in the one experiment. We need to do some significance testing to find out which of these anomalies are interesting and which are just random variability, and then have a look at the actual processes which are going on to cause these changes. It's also quite interesting that the same experiment's been done by a team up in Tromsø, and they've been running the same experiments with NORI SM2 without a coupled Greenland ice sheet. So we'll see what the differences are in their results. We're going to add use a more realistic freshwater scenario, using some modelling done by Vio Coulon and others for sort of future changes from Antarctica. And then if we've got time, I don't know if we will or not, then some of the later tier 2 SFIR experiments. So yeah, lots of possibilities. But yeah, it's just preliminary results at the moment. So I shall stop there.
All right, thanks, Dave. Any questions for Dave? Yes, Betty?
Dave, that's very exciting to see Southern Ocean hosing experiments. We often just see North Atlantic. Have you, in your kind of preliminary looks, been able to look at subsurface ocean temperatures in this experiment to see if they're cooling or warming?
Not yet, but because the initial results I've looked at are very similar to lots of other people's Southern Ocean hosing experiments. What you'd normally find is warming at depth when you get the surface cooling. So I'm expecting that we'll see subsurface warming, but yeah, I've not checked for sure yet. If you're interested, there is actually already a paper being published from some of the SFIR results. I think it was out in just the end of last year, showing Antarctic bottom water warming in these SFIR hosing experiments. So that's already been published if you're interested.
Thanks. Any other questions for Dave? I would just say that once you're further along in your analysis, I would love to see more. I know that some hosing experiments were done by collaborators with CSM2. I would love to see the comparison of what happens with NORI SM and what they found. Oh, that's exciting.
Yeah, I think is Andrew Powling doing those ones? Right.
I don't know, but we have a collaborator. Her name, it was a paper led by Tessa Gertzer, and she did this for her PhD with old collaborator Jan Leenerts. So she published on this. It was about 3-4 years ago now.
Okay.
Okay. If there's no other questions, we're going to move on to our next speaker, Joanna.
Oh, okay.
Yes, you're on.
Let me join the meeting. Or do you have my slides?
I
thought it was
have your slides.
Oh wait, I
just downloaded it.
think I can join this meeting. Okay. Okay. Oh. Yep. And then yeah, I'm not a professional at sharing screens. It's really not my skill. Okay.
All right.
And yeah, so I'm going to kind of provide a primer for Bill's talk next. And this is kind of providing an observational framework and kind of insights into why calving might be so complicated and giving it, oh, why can you not see? Why is this so? Yeah, just we'll just do this. That's fine. Yeah, so this is kind of I'm relatively new to SISM and very new, but have been very lucky to work with Bill and kind of devise different ways that we can actually explicitly consider iceberg calving within SISM. And so preliminarily, again, you're a room of ice sheet modelers. You really are interested in process-based work. To understand how these ice sheets change, we need to constrain not only the patterns, but actual processes of flow and fracture. And this figure on the left shows some work that compares modeled and observed stratigraphy along radar profiles, and then using, I believe bicycles is the model that this paper was just submitted by Clara Henry. And so we have a fairly good sense of how to match observations of viscous flow in glacier ice with actual model output, right? That's what you all do all the time. However, once things get into fracture, like this image on the right, things get quite complicated. And that, in large part, is because this physical processes of ice fracture remain very elusive across all spatial and temporal scales. On the microstructural level, which is really where most of the experimental work has been done to constrain how ice fractures and kind of get a mechanistic understanding of this process, we're looking at deformation along individual grains typically. We're really looking at samples that are undergoing stresses and strains that are far lower than what we see in the real ice sheet system, right? These are occurring over maybe days or weeks rather than the timescales of decades or centuries that you're running SISM at, right? And so resolving that with kind of the continuum processes that are prescribed into these numerical models and higher order ice sheet models is quite complicated, and then also presents the really annoying framework of dealing with which fracture mechanics kind of prescription do you want to think about? Are we working with the linear elastic framework? Are we thinking about this as an elastic process? It's really not very helpful to understand this process that at some level is really operating in a mesoscale from either a macro or microstructural process. So what we can do, at least observationally, is use the efforts that have been made to characterize calving styles using observational data. And so on one hand, we all have seen kind of the explosive disintegration of Larsen B happening very quickly with 2 data points of observation, right? That's led to really decades of work thinking about how this happened. Kind of in the middle there, we have this just sustained calving of icebergs that's really typical of Greenland or places like Thwaites, where there's regular calving of small icebergs over months, and it's just it's a quite regular process. And then finally, the rifting of large tabular icebergs, like what we saw in Brunt in the past few years, occurring quite slowly and periodically, or really episodically, over decades, and producing really large icebergs. And so, iceberg calving is, we know, it's a dominant process of mass loss from Antarctica. And this image, this figure from Eric Munoz paper in 2013 is quite old now, but the sentiment is quite important, right? That when partitioning mass loss from the ice shelves, calving explicitly as a process is about half across the continent. And so this paper, this is like, I think all of you are probably familiar with this paper. It's quite useful to like start your talks with and say why we're motivating this development. But the way calving is treated in this observational study is not actually, it's not actually a physical calving thing. It's just looking at the area, the ice shelf area lost annually. So comparing the extent of Ross in 2012 versus the extent of Ross in 2013. And so this is not explicitly considering calving. It's ignoring our process representation, it's ignoring the mass balance considerations, obviously something quite important in how these numerical models are built. And it ignores this dynamic response of if you lose ice, what happens to buttressing. And so even on the observational side of things, calving is quite frustrating and complicated and hasn't really made a ton of advances. So I think that this, recognizing that this figure isn't actually even considering calving, it's just saying the loss of ice that's not melting is quite important. And so to provide kind of more context of from the observational side of things, I think learning about SISM, it's been really interesting to see how difficult it is to do an apples to apples comparison of a model output and observational data. I guess likely you all will know that already, but it's been very eye-opening for me. And so here, this is the measures data set from Eric Munoz group, right? Looking at ice velocity maps. And these observations typically provide a mosaic of an annual state. These are really stitched together from different sensors with different acquisition paths, look angles, heading, timing. And so this creates kind of this creates an incomplete picture and a really oddly biased result. So if you look up top, those 4 panels are showing 4 different satellite radars. You can see that there's certain places that we really don't get a lot of attention that get a ton of coverage, kind of the interior of East Antarctica, lots of repeat imagery, places like the Amundsen Sea embayment kind of interior area. But then the coasts actually get really limited coverage. And that's in large part because synthetic aperture radar ice velocity has a really hard time resolving the edge of the continent. It becomes quite messy to do those derivations or just derive that displacement map. So all this to say is that while things are getting better and more spatially comprehensive, this GIF is really crazy to me. This is the data that was input to used to make velocity maps for Antarctica from 2005 to 2016. And the spatial inconsistency is quite remarkable, right? So next year, 2011 to 2012, you've got really nothing going on. And while this is generally getting better with time, we still are, Antarctica is still a place where people don't live. And so it's not an acquisition target for commercial satellites or really missions for the most part, with the exception of ISAT-2. And again, like a long time coming has been the promise of NISAR, the NASA's SAR satellite. Don't giggle, it's maybe one day. I'm still holding on hope. And when that launches, it'll be left looking and could provide repeat acquisitions over Antarctica to make velocity maps for every 12 days. So there's hope. But something that we know quite well for Greenland and mountain glaciers, and I mean, Samara's talk earlier, that was the first question, like how are we incorporating seasonality, is that we're just starting to realize that there's really interesting variability on that subseasonal and seasonal scale within Antarctica. So here is just showing 8 different glaciers, kind of a satellite observational time series of velocity across these Antarctic glaciers in the peninsula. And you can see that once Sentinel-1 launched in 2017 or in 2016, things became a lot more temporally dense. But you can also see the error bars are quite huge, and without those red means of velocity, you might just draw a straight line across them. So still the kind of picture of seasonality in Antarctica is still coming together quite slowly relative to places like the Himalaya and Greenland and Alaska. And so what Bill and I have been talking about is how we actually need to explicitly consider calving rather than just saying, ice is thin, and so that cell is gone. And we can use the observational record to kind of constrain a data-driven pattern of annual change. And that can help us get bounds on the cycles of advance and retreat. And so there's certain places in Antarctica where we have kind of a bizarre record of observations. This figure on the left is from the Amory ice shelf. And ice shelves, they kind of come afloat, sitting over the open ocean, and like a cantilever, they kind of thin until they can no longer support their own weight, and then calve off, and then advance again. And so that cycle is supposedly occurring on a 40 to 100-year period and is invariant of kind of climate variability, right? Should just be driven by internal glaciological stresses and the ice thickness. So in Amory, you can see that from 1936 to 2000, there's about 60 kilometers in that ice front variability. Similarly for Brunt, we have the Shackleton expedition mapped the front of the Brunt ice shelf, and so that's 110 years ago now. And so that's about 100 kilometers in our extent of Stancomb Wills and Brunt that's been constrained by shipboard observation. And so that kind of, if we take that information as kind of internal glaciological stresses, we can kind of do something with it. And so I presented on this in June, and so I won't talk too much about it now, but this is a kind of short study that some collaborators and I did where we took decades of observational data, about 50 years, to constrain a simple probabilistic model for expected iceberg calving size. So we took 50 years of data and looked at large icebergs. I'm sure many of you kind of hold near and dear the textbook Willoughby and Long. Actually, maybe not, because this is not an electrical engineering group, but wow. So I'll just move on. But there's basically the main microwave remote sensing textbook. The guy's primary research, the author's primary research is iceberg tracking. And the temporal kind of resolution is quite dense. It's never really more than a day of these observations. And so you can get this first date of appearance of a large iceberg and say that's a proxy for calving, because we're getting tons of repeat acquisitions across the coast. And so we can say that iceberg is basically a calving event, and we can use extreme value theory to assess the likelihood of an annual maxima. So this is just a map in this database of 650 icebergs larger than at least 5 nautical miles along one axis. These are the largest from the 47 years. And so what we're able to do with this simple generalized extreme value model is create recurrence intervals for these expected future iceberg sizes. So we can say that we expect to see an iceberg like the one that calved off of Ronnie in 2017 every 10 years, like the one that calved off of Ross in 2019 every 5 years, and give us kind of a nice rate of icebergs and calving events on an annual scale, which is quite useful for something like SISM, right? And so Bill will get much more into the development side of things, which is really much more interesting and exciting. But using this kind of stochastic model that's been actually constrained by observations, we can now kind of explicitly consider calving rather than say ice is lost in this mysterious way that we need to figure out eventually and kick the can down the road. So we're able to say this is an annual decadal calving rate. And so I just plotted up, Bill and I were talking about how it'd be great to look at this Regnault plot using SISM and kind of mapping out the partitioning between calving and melting through time. And so these are just the mass loss across the continent from calving and basal melt in the dashed line from a recent kind of stochastic calving parameterization that Bill will get into next. But it's really exciting to me that we're able to use observations to inform this model development kind of for the first time in a meaningful way. So thank you. And Bill, oh wait, no, I had one more slide. Oh my gosh, that was like kind of the thoughtful takeaway that modeling these physical systems actually is useful with observational data to give us a statistical approach. I think that as a process-based person, I find it really hard when you're just given a data-driven solution. But that's been fine for numerical weather prediction for a while now. And so if we're just at a point in glaciology where we can do minor things like this to explicitly consider processes that are too physically complicated to resolve, we should start doing it. So thank you.
Thank you. Any questions for Joanna? Ziki, go ahead.
See here, muted.
Maybe they just clapped.
Yeah. Yeah. Well, we appreciate you, Ziki.
Do you have a question, Ziki, or are you clapping? All right.
Okay.
Keshan, go ahead.
Yeah, really nice. Yeah, really nice talk. I'm when you can you go back to page 8? You show several locations about the time series curve. I observed most of them. They show kind of the seasonal cycles, but you can see the right one, the third. So it looks like very different from others. They have kind of the long-term trend. So do you know what's the is there any physical process or something like that, the instrumental maybe uncertainties there?
So that glacier's right here, and it's quite small and has no shelf. These are all none of these glaciers have any shelf. I'm not quite sure exactly what this glacier in particular is doing that has such a strong acceleration, but it is not uncommon. These are just 8 small glaciers on the peninsula, but many of the other glaciers on the continent have an acceleration in outflow over the past few years. Places like Brunt, after calving has sped up a lot, and yeah, I'm not so sure what the physical mechanism is for this specific glacier.
Okay, yeah, thank you. Yeah, I observed that particularly the rate of the amplitude for that location is larger, much larger than other side.
Yeah, it's still useful to see that the uncertainty bars are quite large, and it's a very small glacier, and the speckle tracking approach, or like the way that these velocity are made, requires basically pretty solid signal to noise that isn't really easy to resolve in wet glacier environments like we see on the peninsula.
Okay, yeah, thank you so much.
Okay, I think you wanted to clap. Dave, go ahead.
Hi, yeah, thanks. Super interesting talk. If we're thinking about calving as some sort of stochastic process for these event magnitudes, could you also consider recent calving events? Does that modify the likelihood of there being another calving event of a certain magnitude? Like if you've already had an iceberg recently carved off from that ice shelf, does it make it more or less likely that another big one will be carved off?
So
can you consider that?
yeah, you again, like this is kind of that's a very good question. There's the primary kind of the first order control on calving from like an observational perspective beyond like the glaciological stresses is just the buttressing, right? And so typically once a large calving event happens, the ice is quite buttressed, I guess, back there. So it's unlikely to get another one right away. And that is definitely something to consider in what Bill will talk about next.
Okay, I'll wait for the next talk.
Yeah. Thank you.
All right, well, since everybody's waiting for Bill's talk to answer some of this question, let's move to Bill. Would you like me to present your slide, or you want to present?
Why don't you go ahead?
Yep. Go ahead. Okay. All right. So I present this as a PDF.
You can do like one of the arrows.
I'll try.
Go down. You guys wanna?
I can try mine if you'd rather.
Yeah.
Yeah.
How do we put this?
Okay, so
Yeah.
Oh, wait, no.
I don't know if we,
No, I just can't remember which one it was.
There it is.
Okay.
and then let's see if there's a play button.
Screen.
Oh, it's in preview.
Yeah, if you click the right arrow, it should advance into the full page. Yes.
I mean, it's pretty good.
Is that
We're just looking for like a slideshow view. I'm not sure if preview does that. You go ahead and do this real quick.
or should we just share the PowerPoint instead? Okay, there we go. All right. Okay, so this is work done. Is that going to advance all the time?
Oh, I don't know.
Okay. This is work done in collaboration with Gunter here and Joanna, who just gave a great introduction to what I'd like to talk about. And just as to start things off, as others have said, about half the annual ice loss from the Antarctic ice sheet is from calving, with the rest mostly being from subshelf melting. Similar for Greenland, but the focus here will be on Antarctica because calving in Greenland looks a lot different. So with Antarctica, you have these large shelves, in particular the Filchner-Ronne and the Ross Shelf, which are about the size of Texas, each of them. And then you have shelves of all sorts of different sizes around the margin. You have the Larsen Sea out on the Antarctic Peninsula and the Amory Ice Shelf over on the eastern side. And in the Amundsen Sea, you have lots of small shelves, including Getz and Thwaites and Pine Island. And you also have regions of coast where there are few or no ice shelves, like Enderby Land up in the top right and Wilkes Land in the lower right. And then in Queen Maud Land at the top, lots of small to medium-sized shelves. And what you'd like to have is a calving law that will produce these shelves exactly where shelves are present, and also not produce shelves where shelves are absent. And to do both of those things at once turns out to be pretty challenging. But I'd like to talk about an approach that we've come up with that does pretty well at that. And as motivation, going back to the talk that Tim gave earlier, he showed some results of Antarctic simulations out in the future where you have collapse of the Pine Island and Thwaites glacier basins. And in those simulations that were published in the paper this year, you have a large ice shelf that forms where there used to be grounded ice. And this ice shelf provides lots of buttressing to the upstream ice. And although there was collapse, the collapse is slowed down by the presence of this buttressing shelf. But we have no particular reason to think that that large shelf would be there as opposed to not there. And so if the shelf were to, if that shelf were to calve, it would not buttress as much, and then the collapse would likely be accelerated. So this is a practical reason for having more realistic calving laws and models rather than just using a mask based on present day, which can bias future simulations. So Gunter and I participated using CISM in the Calving MIP project, which is an international model and comparison coordinated by Jim Jordan as part of the EU Protect project. And the phase one of calving MIP was focused not so much on realistic calving laws as on calving algorithms. The idea being that the first step is to make sure our numerics is working as we think it should before we get on to more realistic physics. And so there are two main experimental domains in calving MIP, a circular domain and a so-called Thule domain illustrated here. For the circular domain, the grounded ice is orange and it's surrounded by this sort of a gray-blue ice shelf, and you have a prescribed calving rate which makes the shelf shrink for 500 years and then it expands again for the next 500 years. And similarly for the Thule shelf, which is a little bit more topographically interesting, you start off with a large shelf and then you make it shrink for 500 years, as illustrated in the 3 bottom panels, and then expand again. And after a lot of work in our numerics, we were able to get, for the circular shelf, a very symmetric calving, retreat, and advance rate at very close to the analytical rate which was prescribed. And for Thule, there's no analytical solution, but still we're able to get something that looks pretty similar to what the other well-tested models are doing. So we're pretty happy with our calving numerics now. Just to say a few words about how those numerics work. The basic problem you have with calving, where you have a grid cells of say 4 or 8 kilometers, is how to represent a cell that's let's say is where you have the ice thickness is similar to the ice thickness upstream, but only half the cell is full, because the ice sheet model will typically represent that as, let's say, a wholly covered cell with 100-meter ice when it should be a half covered cell with 200 meters of ice. So what we do is we assign to calving front cells an effective thickness, which is derived from the upstream thickness. And we say the cell is either partial or full, depending on how the effective the state variable thickness or the average thickness over that area relates to the effective thickness. And where we have a partial cell, we don't let ice flow out of it. We just accumulate ice in those cells until it reaches the thickness of the upstream cell. And in the meantime, we use a calving law to compute a lateral calving rate called L, and we convert that calving rate to a thinning rate, the HDT. So it's possible to reach a steady state, for example, where as you have ice advected in, you have a thinning rate, which is a surrogate for calving, which is thinning the ice as it enters the cell, and you can maintain a calving front then in a stationary position. So our candidate law for the Antarctic ice sheet, after trying a lot of things by trial and error, what we found works best of all the things we've tried is a calving law that says the lateral calving rate is equal to the ice speed at the calving front, multiplied by an effective calving stress, denoted here by sigma, divided by a threshold stress, which is just an empirical value that we choose because it works well. And we define the effective stress as a weighted sum of the 2 principal eigenvalues of the horizontal stress tensor, denoted as tau1 and tau2. Tau1 is the along flow stress and tau2 is the across flow stress. And what we find empirically is that the places that have a large tau2 are the places where calving fronts tend to form. And so for that reason, we give tau2 full weighting, and we make that constant C1 a number less than 1, because tau1 is less efficacious in calving. And we found typical values of around 0.2 or 0.3 work well for this weighting factor. And then the threshold thickness, depending on particular model details, something around 50 kilopascals or a bit more seems to work well as a threshold for calving. So the idea here is that when you have an effective calving thickness exactly at the threshold, the lateral calving rate will be exactly equal to the ice speed, and therefore calving will balance advection. Whereas if sigma is larger, then the calving in the front will retreat, and hopefully you reach a steady state. And just to make sure that our tau1 and tau2 values generated by the model are realistic, Joanna created this plot where she plotted up tau1 and tau2 using this measures velocity data. And that's compared to SISM on the same color scale. Red on this scale is positive and blue is negative. So you can see instantly that the tau1 is positive almost everywhere, meaning the along flow stresses are tensile in a positive sense, whereas tau2 in most of the ice sheet is negative, meaning those across flow stresses tend to be compressive. I don't know if you can see this at all, but if you blow this up or squint, you would be able to see for SISM tau2 that at the edge of the Ronnie shelf and the Ross shelf and some of the other shelves, tau2 actually becomes positive. It becomes several tens of thousands of pascals near the Ross and Filchner-Ronnie and other calving fronts. And that's basically why this works, is because the model wants to produce a positive tau2 when the ice shelf reaches a region where it's not constrained anymore by the topography and it wants to expand. So then a comparison with observations. This is results from a 5,000-year SISM spin-up, configured very much as Tim's steady state spin-ups were described. The left is the model result, and the hope is that if you don't know Antarctica super well, that if you look at those ice shelves shown in yellow, that will look to you like Antarctica, even though the shelves are generated, the shelf extent is generated by the model and not by the observations. If you know the continent a little bit better, you can see some biases, and those are illustrated in the panel on the right, where yellow is a region. If you're around the margin, yellow is a region where you have an ice shelf that you don't want one, and purple is a region where the ice shelf is retreated, where you would prefer that it hasn't. So going around the edge, you can see if you can see my cursor, the Rani advances here in the west. This is the Brun ice shelf where it doesn't want to be its full extent. And then over here, the Amory doesn't want to be quite as large as it in fact is. And over here at the Ross also is retreated farther than we would like, while over here the Getz shelf is advanced. Nevertheless, this is really good, I think, for a simple parameterization that in effect has just these two tuning parameters. It has the threshold and then the weighting of the tau 1. And so this is certainly not a unique way to generate a realistic calving front, but the fact that it's pretty good suggests that it's a good start for putting into models and then running the models into the future and seeing how these shelves would respond to future warming that would drive thinning of ice shelves. But that's a steady state deterministic law. And what we'd like to make this more realistic is a stochastic calving law, where calving events, instead of going on all the time at a steady rate, are probabilistic, and maybe you have different sizes of icebergs calving at different frequencies. And so the basic idea that I've been trying is, in a particular grid cell, the calving front, in a particular model time step, there's a certain probability of a calving event during that time step. And the idea is that you have this 1 minus an exponential function. So the quantity on the right looks pretty similar to the equation for the deterministic calving rate, but in this case, it's part of a probability where if you have a long time step with a high stress and a large speed, then that exponential will go to 0, and then the probability will approach 1. Whereas if you have a very low stress, the probability will approach 0. And you just have a random number generated in your code to calve ice with that probability. And the goal is to start from this more simple approach and extend it with input from observations through the collaboration with Joanna to have a size distribution of icebergs, including large tabular icebergs. But that's assuming that we can get this to work reasonably. And we're not quite there yet. On the left is output from the model 1,000 years in. And on the right, you can see that 1,000 years in, you have a lot of biases that are larger than you would like. You have a lot of retreat for the big shelves. And then you have a lot of advance where you don't want it, like Enderby and Wilkes and over in the Amundsen Sea. And this gets worse over time. So there's something about the way this is implemented or formulated that's not quite right. And my intuition is that something like this should be able to work, but that's what we'll work on next. So just to wrap up, we have this new calving algorithm, which we've applied in calving MIP phase 1, which is working very well. And given that algorithm, we've implemented a stress-based calving law that works really well for Antarctica and will be supported in future code releases and applied to ice sheet retreat experiments and ongoing work on the stochastic part of it. Thanks.
Thanks, Leo. I was about to ask any questions for Bill, and yes, Lev, go ahead.
Hi, Bill. One thing I'm wondering is why there's no temperature dependence, like you're basically ignoring hydrofracturing, water collecting in crevices. And that might work for present day, but under a global warming scenario, I suspect you might be tuning to a very different state.
Oh, that's a really good point. You said, why? Sorry, the first part you said, why is there no dependence on?
Temperature. Like basically meltwater production, collection of meltwater in crevices.
The reason is just because one has to start somewhere, and this is
okay.
So the idea is to see how far can we get, assuming it is mainly dynamics. There's no reason you couldn't, for example, if you're, like, say, you're coupling this in a climate model that's forecasting temperature rises, you could put in another damage term related to water on the surface, for example, and add hydrofracture, but that would just be in addition to the model. But you're right. This would be very conservative in a warming climate.
Great.
Okay. Tim, go ahead.
Hi. It's a great talk, and also to the one from Joanne just now. And I have a question to maybe Joanne as well, related to some of the results that you showed. So I remember the measure data set with observed velocities, if I believe, that are turned into these principal stress eigenvalues. What did you do with viscosity in this calculation?
For just the map in Beanstalk?
Yeah.
I just did a really simple, like the most simple version of lens flow law implementation. I believe the viscosity was like the 13th, like the -13th. This was a 6 lines of code.
So it's like a uniform velocity.
Yeah, yeah,
Okay.
uniform. Yeah, this was a very simple translation.
Okay, I'll check. I see.
Could be made more complicated easily. So, yeah.
Okay, any more questions? All right, Heiko just joined, and so yeah, Heiko, if you're still willing to give your talk, you're more than welcome to.
Yeah, can you hear me?
Yes.
Okay, first of all, apologies. I'm really sorry I missed that. I'm on a project meeting here in Belgium, and things didn't work out as expected. But if okay, yeah, then I would try to show my presentation. Oh no, I have to first agree to something here. I hope this will work.
Opposite.
Yeah, Heiko is going to talk to us about Greenland and the impact of resolution, Greenland modeling.
Yeah, sorry about that. I think I'm not really able to share. Where am I? Are you seeing my screen now?
Yes. There you go.
All right. Then apologies again. Gunther always invites to this meeting saying we could also present unpolished work. So I took him at face value. And so this is not really a work. It's more like an experiment. The idea is to look a bit into the resolution dependence of SysEnt Greenland initializations and projections. And this basically started from the practice that I like to follow, which is often running an ice sheet model in different resolutions, like often testing at a very low resolution, slowly increasing resolution to then doing production runs at higher resolution. And so that made that we are basically always running with a certain range of horizontal resolutions with the model, and also, yeah, presenting them side by side. So that, yeah, also helps to test the ice sheet model over a larger range of horizontal resolutions and seeing if the forcing approaches that we use are kind of independent. In this particular case, I also made use of leftover CPU hours that I always have at the end of or often have at the end of the allocation periods. So I could use that to run especially the high resolution simulations that otherwise would maybe feel a bit expensive to put in. And overall, the idea of this for me is to work towards a multi-resolution setup. So this idea that you could start on a low resolution, for instance, with a paleo simulation or a glacial interglacial spin up, where you need low resolution to be able to get through the years, and then consecutively switch to higher resolution. So that's kind of like my perspective of where I would like to go with this. But first I want to just show a few different initializations with different resolutions. And the process of the initialization is not something that I have invented, it's something that Bill has created. And so the approach is to spin up the ice sheet with annual mean surface mass and surface temperature for, in this case, 5,000 years. So this is about what you need to bring the geometry into shape and also bring the thermodynamic evolution forward. And here are some examples of figures, what is going into that. So on the left-hand side, you have the surface mass bands in millimeter water equivalent per year. In the center, you see a field of basal friction that is, or basal friction parameter that is kind of the result of the inversion process. And on the right-hand side is the target surface elevation. And the surface elevation is really the quantity that is calibrated for. So the calibration process is adjusting basal friction parameters locally to match the observed surface elevation. And this is kind of an iterative process following Pollard and DeConto, where you adjust these parameters in a forward simulation and basically hold back ice when you need more at that point, or make it more slippery at the base to evacuate ice more quickly from a certain point. And then after that, I always like to run a relaxation experiment. So then keeping these basal friction parameters constant and just running the ice sheet model forward with the SMB, the prescribed SMB, to see basically what residual model drift you have and if you're in a kind of stable situation. For Greenland, that's typically the case. And maybe just interesting to mention is that the velocity is also quite well matched, even if it is not explicitly calibrated for. So you can see here on the left, it's on the right, but in the left panel, simulated velocity compared to observed velocity in the center, and the difference. And I mean, it's maybe not that surprising that when you match the geometry, that the velocity is also well captured, but it's notable anyway. By the way, excuse me, these figures are all out of a paper that our PhD student Charlotte Ralves is publishing, and has been accepted and will soon come out in the cryosphere if you want to have a look at that. It's not about, this paper is not about resolution dependence, but illustrates this initialization process, among other things. So here I have results for doing the same kind of calibration at 5 different horizontal resolutions, from 16 kilometers to 842 and up to 1 kilometer. And yeah, here are some further results. So what you see on this figure is on the top, the mass change over this initialization experiment, so the 5,000 year spin up. And then in this case, I've actually run a relaxation experiment following that for another 5,000 years. But typically we only use the first 500 years of that and then restart our future simulations from that. And the difference between the top and the bottom figure is that on the top, it's just the pure mass of the ice sheet. And on the bottom, I've rescaled that to sea level contribution. What you can note is a bit difficult to see, but what you can note here is that the starting mass is basically at the same time the target mass. So we start from the observed ice sheet geometry, and then the ice sheet in this case gains a bit of mass and then relaxes towards a mass that is a bit below the target, the observations. And this is difficult to see, but the different resolutions also have different initial or target mass, and this is from interpolation processes going to these resolutions. So overall, we find quite similar behavior in these across all these different resolutions. There's a very small remaining drift at the end of the spin-up. So this is like represented in this RELAX experiment here on the right-hand side. And you can see that it's quite similar for the different resolutions. The slope of these curves or the mass trend. Initial target mass is different due to interpolation, and as I've said. And so for 1 and 2 kilometers, they are quite close, which may suggest that there's convergence towards these high resolutions. Although the 1 kilometer is also the resolution of the forcing data set that we use, so this is mass balance forcing. So I have to treat this a bit with care, this convergence finding. So on first view, they look all very similar, these initialized ice sheets. Well, they have all been relaxed to the same observed ice sheet geometry. And so I'm zooming in here to two different regions. So here, this is basically Jakobshafen or Cermak on the different resolutions, just to give an impression of how much detail you can capture on this. And in the bottom right figure, you have the bed machine 5 data. So this is what we use to derive the target geometry. Also on 1 kilometer here, the original data set is in 150 meters resolution, but yeah, here I plotted it out on 1 kilometer. So yeah, obviously you can see increasing detail with the increasing resolution, but overall even the lowest resolution has like a pretty good match for that respective resolution. Here's the other side of the ice sheet, so Kangerlussuaq Glacier, and you can see that on the 16 kilometer you can barely resolve that outlet glacier valley at all. So you need to go to higher resolutions to have like a reasonable simulation. I've also plotted out here the beta. It's on a logarithmic scale to see that better. And also here zooming in to the Neges region, where you can see that the calibration process basically prescribes these very low friction in this area, which is required to evacuate the ice because we're tuning for surface elevation, and leading to that increased velocity in this region. Yeah. So quick word about the projections that follow these initializations. So this is typically what I like to do here, is like initialize the ice sheet and then follow it with projections. And these projections I'm showing here are based on the ISMIP-6 protocol. So just quite generally downscaling climate forcing from coupled climate models from the CMIP archive, downscaling those with regional climate models and using a retreat parameterization for the outlet glaciers, which leads then to standalone ice sheet model projections based on these forcings. And for the interest of time, I will skip over the next 2 parts, which just give more details about how this forcing is constructed. You can go back to that if you want to. I can answer the questions about that. But just to show here for the projection, so this, in my case, consists of 2 parts, like a historical experiment that you see on the left, going from 1960 up to 2015. And then on the right-hand side, the actual projections under this ISMIP protocol. And you can see that for these different resolutions, you actually get quite similar responses, which I think is encouraging, especially if for some test experiments you want to run at a lower resolution, you get more or less reasonable results with that as well. But some or a big part of that resolution independence lies also in how the forcing, the ISMIP forcing, is produced, because at the time we took really care of defining that in a way that it would be largely resolution independent. So it's a combination of the model behaving well also at lower resolution, but also the forcing protocol itself. Yeah, this table I will quickly summarize with the sentence here below. So there's a estimate for the cost of these simulations if you want to see how much you gain when you go to lower resolution. So there's a factor 10 approximately increase in compute cost going from doubling the resolution, and a factor 3 increase in the storage, which is also quite substantial for these 1 kilometer runs. You can see that we need for the whole for one initialization already 120 gigabytes, and then of course for each projection you have additional storage for that. So quick summary, the SISM simulations initialized by calibration to match the observed surface elevation. They work well across a large range of horizontal resolutions. Then I've shown some projections under the ISMIP protocol and also show that those are largely resolution independent. And I don't really know what to do with this work further on, but I would be interested in your comments, and I'm also happy to collaborate and think together about what can be done with this experiment further. So that's all I have. Sorry again for messing up the timing earlier.
Thanks, Heiko. Any questions for Heiko? Yes, go ahead, Keifan.
Yeah, thank you. Good talk. I'm really interested in the map you showed, I think, in the very beginning of your talk about the bed friction parameter map. I see the spatial variations, and I wonder if they're mostly related with the roughness of the topography. I mean, the topography gradient or something else. So that parameter.
Yeah, so in this particular case, the bed friction field that you see is what is needed to minimize the mismatch with the observed surface elevation. And hopefully there would be a relationship to some physical quantity, but probably it's a relationship to several different physical quantities. So if, for instance, in an ice stream, your ice is weakened, and this is not represented in the model, then the calibration of this parameter will pick that up to, to compensate for that. So it's very difficult to assign the meaning of this friction field or parameter field that we derive to a specific physical quantity, because it's, in this sense, it's kind of machine learning. If you want, you have a certain target that you want to reach, you choose this one parameter that you minimize or maximize for that, and that's what comes out. But hopefully, looking at those fields, one could, learn something from it and maybe derive a more physical base, at least to some aspect of that parameterization. But yeah, so yeah, that's kind of how it works.
Yeah, I see. So yeah. So that parameter is generally you tuned in the model, right? Just based on the bias between the observation and the model, you tuned that parameter in the model, not reconstruct from other physical process.
Yeah, so it's quite common to do that, so it's not unusual what I'm doing, but it's important to say that there are also quite different approaches to set this parameter globally or set it according to, the proximity to the coast, for instance, because you expect to have more slipperiness where the bed is in contact with the ocean or something like that. So I imagine, for instance, I see Lev has a question here. I imagine that Lev does not spatially explicitly tune that parameter, but rather finds like a global tuning. And in a sense, that's the more physical approach, I would say, that you try to, find an expression for that friction in like you suggested, in like bed properties, maybe where there's a confluence of basal meltwater. I don't know, whatever based on the sediment, something like that. That would be the more physical approach. But in this case, where we are interested in, doing projections over centennial timescale, it may be the more appropriate thing to kind of basically solve that initial value problem and kind of come with an initial state that represents the geometry and the velocity very well. I wouldn't trust that, to run for 10,000 years, because then that the bed friction structure would probably change with, changing sediment or a changing ice sheet geometry.
Yeah, I see. Thank you. The reason I ask this is I think most coupled GIA and ice sheet model, they only consider the vertical variation for the topography. Actually, GIA model, they also have the horizontal motion. So this will change the roughness or the gradient of the topography. So I think that maybe it's true, or maybe we can just look into it further about those kind of bad friction parameters.
Yeah, that's an interesting perspective, how I never thought about how the isostatic adjustment would change the properties of the bed. Yeah, I think that's interesting.
Thank you.
Thanks.
Leif, go ahead.
Yeah, I'm going always for a bit longer time scale. So Heiko, your resolution in the convergence, or like that fast convergence, I suspect is partly due to kind of the short time scale. And it'd be interesting to see if you could take it to longer more like maybe like deglacial intervals to see what happens. And also I'd be curious to see isolation of the dynamic part, resolving the ice flow at high resolution versus resolving the surface mass balance at high resolution, to isolate those two components. Because when we're doing, my interest is glacial cycle integrations, and we're not going to be doing 1 or even 5 kilometer resolution if we're doing ensembles. So finding out exactly what resolution we need, how can we maybe compensate for it, I think would be really useful.
Yeah, thanks. I think that's what I started the introduction with. That's really my goal, to kind of go from a very low resolution to begin with. Let's say 16 kilometers, and do kind of glacial interglacial spin-ups, like to have kind of long-term memory in the ice sheet, and then maybe move to higher resolution as we go forward. That I think is promising to do, seeing that the ice sheet behaves quite consistently across these resolutions. But your other point is well taken, that not all parts of the model have to be run at super high resolution, and I acknowledge that running at this 1 kilometer resolution I can only do because I have some leftover. I mean, I wouldn't really propose a project running everything at 1 kilometer. I think it's fairly exaggerated for the amount of detail you can actually produce from that. But yeah, that would be interesting to look a bit more like what actually needs the resolution and what doesn't. Thanks.
Are there any questions in the room? No? Okay. Thanks again to all the speakers. I know based on the schedule, we're a bit we're running late, but that's okay. It's just us, right? And for the next slot here is destined for some discussions. And again, so the development of CISM, whether as a standalone model or within CSM, is a community effort. So the community input is very important to first want to make the model better, to make it more user-friendly, to advance our science. So every topic is on the table. And if no one has a specific topic that they'd like to discuss at this point, there's a few items that would be interested in hearing from you. So I'm going to start by opening it up as a general item. if anybody would like to take an opportunity to engage in any discussion, whether it's like technical, scientific, anything. Yes, Betty.
I had a question for Kate, because I was really excited about your talk about the solid earth and implementing it. How long before you think it will be far enough along that we'll start changing? How did you put it? What the surface sees and is, paleo, the geography, in other words, coastal geography.
I think that's going to take a minute. So the the early goals, and by a minute I mean probably a year. The early goals are to be able to build and run within the CESM framework, and then like Keishwan was showing, the actual coupling between the ice sheet and the GIA model will be the first target. And that's not something that's been done very often. So I imagine that will involve some iteration. But my ultimate goal is to be able to have that variable topography. I don't think it's going to be involved in the CMIP 7 simulations, but maybe CMIP 8.
And geography, not just, I don't know your definition of topography, I just think of mountains, but also the geography of like Bangladesh.
Yeah, absolutely. So, all of the masks are static in CESM right now, which is an issue for these long transient paleoclimate runs. And I definitely think that CLM could look into the vegetation changes resulting from these changes as well. I mean, I think there's a lot of places where we need to be more transient in the surface of the model. I don't know what we would tackle first. It would definitely be, I think, community driven in some ways at that point, although I really hope that we fix the atmospheric surface. Yeah.
All right, I'm going to bring up just one slide that has like 3 items that we would love to hear from you, if you have, of course, an opinion. And so it's about the user experience in CISM for pre and post processing, running CISM standalone in the CSM framework, and experience with the bulletin board. So I'm going to start with the last point, actually, because it might be the fastest. Does everybody know that we actually have a bulletin board where you can post questions and get help?
No, I didn't know that.
Okay.
You didn't put the link up.
Okay. Is it the same? So this was the in the room answer. And what about online? Does anybody?
Yeah.
If you know, put a thumbs up.
No.
No thumbs up. Okay. So we do, and I need to. Okay, maybe we need to be better at communicating about this. So typically, what happens is that that when people have questions, of course, they email us directly, and we provide answers. And when we're trying to slowly move away from this, so that whenever there's the same question appearing over and over, we don't have to write the same answer over and over. People can just go to this bulletin board and say, "Oh, this question was asked before." But maybe the community is growing, and it was small enough that we were doing it. But now, okay, we're going to try to move further along with using this bulletin board of practice. Yeah, I guess we need to be better at communicating about it. So noted.
I have something, Gunter.
Yes.
Not always known by the community. It'd be great if the community answers some of the questions too. If you have answers to someone's question.
Yeah, definitely.
Yeah, I should add that this bulletin board is indexed by Google. So if you search for, say, a build error in CSM, or it usually comes up with the bulletin board post. Somebody else has already seen that build error, and you can see what worked for them. CISM has its own section, so it's a big bulletin board for all of CSM, and Land Ice and CISM has its own section. that admittedly hasn't been used as much as some of the other component models. So I think that it would be nice to try to fill that out a little bit more. It might be that you guys see from Gunter and I in the future things like, here, I'll give you the answer to that question, but maybe you could make a post on the bulletin board with this error in your solution so that other people can see it.
And I'll add to this, like if we ask you to post it there, it's not just to annoy you, really, it might sound annoying to you, but it's really to improve the community of practice and have like information being able to be more visible to everybody. Okay, so that was quick. Then, so as Kate alluded in her talk, CISM can be run on your laptop just with the CISM code. And we wanted to see how the community feels about running CISM standalone within the CSM framework. First, I said, like, maybe you're not very experienced with when we're running within the CSM framework to begin with. But we would like to get a sense of your thoughts on switching to this approach.
So you're meaning like running CISM in the way that we typically would run the whole CSM model, right?
In a TG comp set way, for example.
Okay. I think it sounds good. Like there's maybe more documentation at large on running the larger framework. So as somebody who is interested in running CISM that doesn't have any background maybe with Fortran, looking at those tools for running the larger framework could be better, I think.
Okay. Summer, you had your hands up?
Yeah, I had a similar question. Are you specifically asking about CISM standalone or coupled with other components of CSM? And if it is standalone within the CSM framework, then are there any pros and cons to that?
So it would be CISM standalone within the CSM framework. And the pros that I've imagined is that basically what I'm saying is that you can do your CISM experiment. You can take notes, I'll just lean in. You can do your CISM experiment using the case control system of CSM, which means you can set up an entire experiment and run it using about 4 commands. And you would have the machines that are supported by NCAR always updated. You wouldn't have to necessarily maintain your own build scripts the way that we do in CISM right now. And then each case has, if you've ever run a case in CSM, they have a case status and a README and files that specifically describe for this experiment what the software was used to run it and where all of the results went and how they were, like what version of code was used to create it. All of that is documented within the case. So there's a lot of positives there. The cons would be that if you're used to building and running CISM, it is very fast to do the standalone. So now you have to learn a whole new system. The case control system allows you to add I'm gonna say nameless file. So it uses a nameless specification instead of the specific CISM configuration file. We're trying to merge those together as best we can, but it might be a slightly different configuration system through CESM. And there might be other sort of small differences in how you would set up a CISM standalone versus a CSM, but I'm not like coming to my mind while everybody's staring at me right now.
Does it make any difference to input and output processing?
So what I'm working on right now is to make sure that the CISM input and output is done the same way from the CESM side. Yes, currently in CESM, the input and output flows through a different path to get to CISM, but I have plans to change that. And it wouldn't necessarily be, so like SISM running in a fully coupled simulation needs to have that difference. But if we're doing like testing or experiment building or development, it doesn't. So that's why I imagine this as being sort of a different type of comp set that supports this sort of SISM standalone with the CESM front end.
So for example, say we want to do one of these glacier simulations for a large glacier region. We want to read in, say, the RGI, so something derived from the RGI outlines or the consensus thicknesses. Those would live where, those data sets would live where exactly?
So they would probably go into your run directory. So you could have them, you know, in your wherever you keep your data sets on Cheyenne, sorry, Duratio. And then you would need to move them into your run directory so that they can be found by the CESM experiment. There is a capability of CESM to automatically go and grab data for you. So we could leverage that, but you need to put the data in the right place for it to be able to find it. So it's kind of up to you how we want to go about activities.
But during the run, SISM would access those files just as standalone SISM does,
Yes.
without having to receive things through the coupler.
Right.
And that's what you're enabling now, because other components don't do that typically.
Right. I mean, I can think of examples actually where components do sort of randomly grab files from different places. It's not.
I think that's what I've been doing with CDSM, but standalone CDSM runs, just grabbing files. Are you all saying within CSM framework?
Yeah.
Can't grab files from random places.
Yeah, I mean, and then you move them into your run directory by hand, or does it just find? It should just find them. I guess you could point to them in different places. This is what I've done in a few places where you just sort of point to a file that's on Duratio and it will work, but it's not really a long-term solution. If somebody else gets that code, they're going to need to be able to find that file, and having a path on Duratio isn't a great idea. So that's why you would put it into the input data repository for CESM, which would be automatically pulled for anybody else using that code going forward. But that probably isn't something you want to do while you're just developing your
But one thing we've talked about is that when we're running, say, in a high resolution domain, like if we want to do high mountain Asia, we have an input data set that might be a grid that's 30,000 by 30,000. And that's a lot for one processor too. So we can have it take advantage of CESM's parallel IO.
Yeah, so that's true. We have all of the file input output libraries available to us. And if we build that in so that system can see that from the CESM side, then we could probably use it. That might be a stage 2 option.
We'll get there.
Yeah.
Not in the next 2 weeks.
No.
Okay. And yeah, it's 12:30. I'm pretty sure people are hungry. So we're going to leave the user experience when we're maybe more advanced in our tools for SISM use. Thank you everyone for attending this meeting. And for the great talks. And hopefully we'll see you again, everybody, this summer for the CSM workshop in person, if you can. And for whoever is here in person, if you can join us for lunch, that would be great. But yeah, thank you, everyone. Have a great rest of your week.
You have another con.